Hello students, today we are discussing about some of the important tips and important topics from the chemistry. If you talk about MCQ point of view in your CET, the chemistry has weightage of around 50 MCQs that you have to deal with in 45 minutes. That means for a single question, we have less than a minute. That means we have to utilize this time properly so that we can attempt all the question with the proper best ever answer. Now, our chemistry has been divided into two parts, like we have a paper 1 and we have a paper 2. Let us first only talk about the chemistry paper 1. Now from the chemistry paper 1, that student must go for these chapters. They are the most important one. Is the first one thermodynamics. Thermodynamics is having the highest weightage in the chemistry. It's around 50% of that MCQs will be asked on the thermodynamics. That will be consisting of some theory questions or maybe some numericals will be included in this. The second chapter that students should focus on is solid state, which is counting around 8% of the MCQs. Next is solution and colligative property. Which is having weightage of around 8% again. Then fourth chapter, electrochemistry. Not having much weightage, but I'll say around 6%, even less than 6% can be considered. And we have kinetics. It's around 5%. So these are the most important chapters that students should focus on in your paper 1. If you talk about this particular questions, you'll also see these chapters are having the numericals. So while doing the revision of this chapter, student can first of all, I will recommend you to go through your textbook, go through the theory of the textbook, all the definitions and all, you can just point it out. And then you can make a note which is related to the formulae. You can collect all the formulae which are related to these chapters. For example, if I talk about this solid state chemistry, we have an important formula, right? Density is equals to Zm upon NaAq. Then if I talk about solution and colligative property, which is including the like elevation in elevation in boiling point or depression in freezing point. So all these formulas we can collect it in one notebook, and while solving the MCQ, whichever new formula you just come across, you can note down that formula also in this notebook. While solving the numericals related to the MCQs, which are special related to the numericals, we have to see that since we have a less than a minute to solve that MCQ, we need to go for such a method that will give us the answer in a very short method. That means including your calculation has to be rounded off, and we can do this calculation. Like for example, if you have this calculation having Avogadro's number, which is 6.023 into 10 raised to 23, which I can round off to 6 into 10 raised to 23 while doing my calculation. So just try to round off the numbers, but don't round off to a bigger number. Make a short round off of that number, and then you can do the shortcut method of that calculation utilize and to get the answer. So you can first of all, for the chapters that you are going to do is, you can make a list of all the formulas in one notebook, and some additional formulas that we study for the CET, that also you can note down in this. Okay, as I said, while doing the calculation for the numerical, use the shortcut method as possible as possible over there, so that you can get your answer in a shortcut manner. Sometimes you'll find in an MCQ where a logical calculation or logical method will also give you the answer, no need of doing the calculations also. Now in your chemistry 1 only, there are 2 more chapters included. First of all, there is chapter called as P block element. Now the weightage of the P block is around 9% in the CET. But the kind of the theory which is involved in P block, it's very difficult to revise over there. It's having lots of inorganic reaction, which is there is no connection of one reaction with other reaction. So in this case, what student can focus is, we have in P block around 4 groups. So when we talk about the P block element, we have 4 groups including 15, 16, 17 and 18. So student can go some important questions related to the P block. Likewise, they can go for trends in their properties, the periodicity properties. So they can go for the periodicity trends. That is very easy or a convenient way to revise in case of P block. Then we can go for the anomalous behavior of the first element. For example, for the 15 there is nitrogen, oxygen, for the 16, 17 there is a fluorine. So they can go for this. In group 18 there is hardly periodicity properties are there. So student can only revise these properties for the group 18, and especially they can focus on some applications of the noble gases for the group 18. In the remaining 3, there are some chemical reactions also involved, but if students can focus on some important topics like hydrides of the group elements, then they can talk about oxy acids, which are related to the phosphorus, sulfur and halogen, then oxides of nitrogen, and some important compounds like they can go for ammonia, HNO3, H2SO4. These are the nitric like acid base reactions. So they can go through some of the reactions related to some important compounds of the chapter. It's really very difficult to revise the P block in one slot because there are lots of inorganic reactions are involved. But at least instead of skipping the entire chapter, I will advise students to at least go through this and try to solve some of the MCQs related to this. So that will really help them and build up their confidence in the P block element. Now let us talk about our paper 2, which is having important chapter. I'll make a list of that again. The first important chapter that student has to do it's alcohol, phenol and ether. That will count around 8% weightage from the CET. Second chapter they should focus on is the coordination compounds. This is also counting around 9%. Then they have nitrogen, organic compounds containing nitrogen, that's around 8%. A lower weightage comparatively, that's for the haloalkanes, that's around 5%, and aldehyde, ketone and the carboxylic acid, that's around 5%. So again, these are the important chapters, and out of these 5, if you'll find, there are 4 chapters which are related to all organic reactions. So I will advise again over here student that they can make a chart for the chemical reaction. Let us say, for example, if they are revising all the reactions related to the haloalkanes, what they can do a chart formation for the reaction. They can collect all the reactions of haloalkanes and they can make a chart for the revision. For example, if I'm talking about the RX, then I should know the role of the reagent that is playing important role over there, because if I know what is the role of the reagent, the predicting the product will become easy for me. For example, if I'm allowing this to react with the aqueous KOH, then this is a replacement of X with OH giving corresponding alcohol. If I'm allowing this to react with ammonia, there is a replacement of X with the NH2 and I'm going to get the corresponding amines. This is alcoholic. But again here I should understand I have to use ammonia in excess, then only I'll be able to get the primary amine. Otherwise it will carry out the reaction further so as to give me secondary, tertiary and the quaternary ammonium salt. If I allow this to react with the sodium alkoxide, then I'm going to get corresponding ether. If I allow this to react with the carboxylic silver salt of carboxylic acid, then this will give me the formation of corresponding esters. So in this way we can form the different compounds from the alkyl halide. So I need to know the role of each and every reagent. So students can make such kind of charts and daily they can revise these charts so as to revise their reagents. And many a times you will find, though we have these 4 chapters together, but there are some reactions common in them. So when you keep on revising yourself with the reagents, there are many things, many a time when you revise one chapter, you are many times revise many reactions from the other chapter also. So a student has to focus on the reagents that they have to revise for the specific reaction. So they can make such kind of charts and they can revise that for themselves. Now, as I told you, in this part there are 5 chapters, that is a condition which is do and die or die. They have to revise this particular 5 chapters. Now the thing that they can skip or they can do a last day revision for the chapters, that are polymers, then chemistry in everyday life, then there is chapter general principle. This chapter they have in chemistry 1, but I'm just listing the chapters that they can do a last day revision for this, because they are the one time you can say revision chapters are there, so they can do the last revision also. Also in paper 2 there are 2 more chapters that is to be included, that is biomolecules, and we have D and F block elements. Now in case of biomolecules, we have lots of bulkier molecules, that structures to be revised, like biomolecules including carbohydrates. Then in carbohydrates we have different type of carbohydrates, then we have a glucose structure, then fructose structure. So now student has to focus on the kind of the linkage is present in the glucose, or kind of a linkage which is present in fructose. When you have a cellulose, just for example, if we talk about the starch we call it as the polymer of the glucose, but it is linkage of alpha D glucopyranose. And when you talk about the cellulose, it's a combination of beta D glucopyranose. So these are the small things that student has to focus on while solving the MCQs, because now the biomolecules, rather than remembering the entire structures and all, the student has to focus on what kind of linkage is present in those structure and what are the highlight features of that structure they have to focus. For example, if they talk about DNA or RNA also, so DNA and RNA they differ in the sugar. For example, in DNA we have deoxyribose sugar, and in RNA we have the ribose sugar. So kind of the difference between small points that has to be remembered, because now when we talk about the biomolecules or polymers or chemistry in everyday life, there are some general knowledge questions may be connected, or they are the chapters which are related to general knowledge, so they can be asked in this time. So these are the chapters we have to read them thoroughly, and the small things, as I said, the linkage or the structures related thing or the properties related things, they have to go through this properly in the from the textbook. About the DNF block element, again I will advise you for the trends in the properties for the DNF block elements, like properties like metallic properties or the color or their catalytic activities. The student has to go through the trends. There are some important topics like lanthanoid contraction and all, they have to focus on that. But if I compare this chapter, compared their weightage compared to the other chapter, they're not that important, but student has to go through it as a last revision. These are the one time revision is enough for it. So for these particular questions, again I'm going to talk about, out of this 50 marks question, you will find a certain question which are really theoretical one. Then there are some questions you will get some related to the numericals, then related to the chemical reactions, and finally there are some questions that can be asked, the memory based questions, like they can ask you related to the you can say the color of the complexes, or the structure related things they can be asked. So if you talk about it, the time consuming questions are the numerical one, where it is going to take time to immediately recollect the formula of that particular numerical, as well as to do the calculation. But though, as I told you, that while doing the numerical calculation, try to round off the numbers and use the shortcut methods to do the calculation to arrive at the right answer. You may find in the options sometimes the options which are given may have a larger difference. Like for example, they must have given 50, then option B is it's like 100, then it's 200, or option D is around 1000. So when you have a large difference, so you can do a tentative calculation so as to at least find out where the answer will be nearby, and you can go ahead with that answer. So try to go for a very shortcut methods to do this numericals. But as I told you, for your 50 minutes numericals, there will be this MCQs, there will be only 45 minutes. Now in this 45 minutes, if you have to finish this all 50 marks question, we have to utilize a maximum time for the numericals over there. So if you need a maximum time for the numericals where you can finish the numerical calculation in a proper way to get the right answer, then you have to reduce the other MCQ time. That is including your theoretical, chemical reaction related things and the memory based questions. So try to reduce the time of the answering over there, so that maximum time you can utilize for the numerical based questions. So see to it right now also, when you are doing the practice for the MCQs, try to see in how much time you're finishing the MCQs. Obviously we have to get the right answer at the end of the time, so getting the right answer in that less than a minute is very important. So while solving the MCQs right now also, when you're doing the practice, I will advise students to solve max to max questions and get the question papers of this, and try to solve your 50 marks chemistry MCQs in 45 minutes. Also we have a combination with other subject also, like physics, where it is going to take time for the numericals, and also we can reduce the time of chemistry and you can give the time to the physics. So this is only possible by max to max practice of this session. So definitely for chemistry 1, as I told you, students can make a notebook for all your formulas collection, and for the chemistry 2, student can make the charts of the chemical reactions or shortcut methods. So they can make these charts and they can keep them with themselves, so that before one day before also they can revise those charts rather than just solving MCQs. We have to of course at the last day practice we have to focus on the theory, so that time you can utilize your notebooks and charts for the last day revision. So right now you can focus on making such things, materials ready for your one day revision. So time management is very important for the solving MCQs, and logical way of solving, that is of course important. So time management, you can do this only by practicing max to max papers of the chemistry and try to solve them in 45 minutes. So time management can be done only by practicing more and more paper. So this is overall the review for your chemistry that has to be done, 50 marks MCQs to be solved in 45 minutes. So today we are going to discuss about the different important reactions of the halogen derivatives of alkanes and arene. So let us first focus on the preparation of the alkyl halides. Now alkyl halides can be prepared from, let's say, alkanes. Now, if you are preparing from the alkanes, there is only one reaction possible, that is RH plus halogenation X2 will give you formation of the RX. Now, here under we have a different condition. For example, instead of the halogen, we can use chlorine. If you are using chlorine, we need a condition like sunlight, or we need a UV light, or we need a high temperature. So all these conditions clearly indicates there is a chlorination, and that will give you the formation of the alkyl chloride. We can also use bromine here, but bromine need anhydrous, else air Br3 as a catalyst over here. But in case of iodine, the reaction is reversible in nature. The reaction is reversible as a byproduct, the HX which you get in this reaction is HI over here, and HI is a strong reducing agent. Hence, we carry out this reaction always in presence of oxidizing agents like HNO3 we can use, or HGO you can use, or HiO3 we can use. While the third point, the last point, that is fluorine. We don't do the fluorination because that's explosive in nature. So we can do the halogenation of alkane to get the corresponding alkyl halides. We can also start from alkenes. That's the another method of preparation for the alkyl halides. Now when we talk about alkenes, there are two conditions under this. Maybe you are taking a symmetrical alkene. If you are taking a symmetrical alkene, let's say R, CH, double bond, CHR, we can add simple HX to this. You will get the formation of the alkyl halide. Because H will go to one carbon and X will go to the other carbon. But if we are having some unsymmetrical alkene over here, then the reaction will take place according to the Markovnikov's rule. For example, if you are having R, CH, double bond, CH2 plus HX, then according to the rule, the negative part of a reagent, that is X, will go to the carbon atom having less number of hydrogen atom. Hence, according to this rule, it is expected to get R, CH, X, CH3. But if we carry out the same reaction in presence of peroxide, also we have to remember the HX has to be HBr. Then rather than getting the secondary alkyl halide, we are expected to get the primary. So rest of the thing we get according to the Markovnikov's rule, but in presence of peroxide it is anti-Markovnikov's rule, or the peroxide effect is followed. This reaction is only valid for HBr, not for HCl, not for the HI, or not for the HF also. We can also start from alcohols, all methods of preparation from the alcohols. Now under alcohols, we can use different reagents. First of all, we can use HX. Now under HX, ROH plus HX will give you formation of the RX with the loss of water molecule. Now here if I use HCl, itself is less reactive and hence need a presence of catalyst like ZnCl2. That's why this reagent is called as Lucas reagent. Then we can use HBr, which don't need any kind of a catalyst, and we can use HI also. So simple heating condition will be enough for them. In case of alcohols, always to be remembered, in case of alcohols, the reactivity is higher for the tertiary, then secondary, and then primary. While in case of HX, we have to remember HI is more reactive than HBr and then HCl. And that's why if you have a combination of primary alcohol and HCl, they are very poor. We need a zinc chloride as a catalyst in this reaction. Then we can also go for the other reagents like PX3. There can be PCl3 or PBr3, or we can go for PI3. So ROH plus PX3 will give you formation of RX with the loss of H3PO3, byproduct as H3PO3. Here PCl3 is easily available in the market. Just heating, refluxing condition will give you corresponding alkyl chloride. But PBr3 and PI3, that is to be prepared in situ by the reaction of red phosphorus with the bromine or iodine. Whichever reagent you want to prepare, accordingly you have to select the reagent. But the best reagent amongst this is SOCl2. If you talk about SOCl2, alcohols reacts with SOCl2 to give the RX, that is alkyl chloride specifically you will get, with the loss of sulfur dioxide and HCl. Since the byproducts in this reaction are both gaseous in nature, this is the best method of preparation for the preparation of alkyl chlorides. And the last one, we can also go for some PX5. In PX5, the one which is readily available in the market is PCl5 only. So ROH plus PCl5 will give you formation of specifically alkyl halide with the byproduct POCl3 and HCl. So these are all methods of preparation from the alcohols. You can go for HX, you can go for PX3, we can go for SOCl2, or we can go for PX5. But out of this, the one which is more efficient is SOCl2. Apart from all these methods, we have two more methods. They are just conversion of one alkyl halide into another alkyl halide. That it's, let's say, Rx dash plus NaI. If I use it, this will specifically convert the alkyl halide into alkyl iodide. This reaction is generally carried out in presence of acetone. This reaction is known as the Finkelstein reaction. In the Finkelstein reaction, the compounds, like when the X dash is a chlorine or bromine, these chlorides and bromide compounds are converted into corresponding iodide compound. Here, the acetone is used as a solvent because during this reaction, the byproduct form is NaX dash. It's insoluble in acetone. So we can just filter the byproduct and we can get the corresponding or required reactant. Now in this case, we can also do the Rx dash reaction with AgF or any other fluoride salts like cobalt fluoride or antimony fluoride or mercury fluoride can be used. This will convert the alkyl halide corresponding to the fluorides. This reaction is called as the Schwarz reaction. So these are all method of preparation of the alkyl halides that we need to focus while revising for the MCQs. Now let us talk about all different reactions of the alkyl halide. Now when we talk about reactions of alkyl halide, if you allow this to react with KOH, we'll take aqueous KOH, there will be just an exchange of nucleophile and you will get formation of corresponding alcohols. So here X is replaced by the OH. Instead of KOH, we can also use moist silver oxide. The meaning of moist silver oxide is AgOH only. So we can have a halogen exchange again with the OH so as to get the formation of alcohols. So to get the alcohols, we have two different methods. Either we can go for aqueous KOH or we can go for the moist silver oxide. If you allow this to react with the KCN, alcoholic KCN, then it will be exchange of X with the cyanide and we'll get corresponding alkyl cyanide. Also, we can have same reaction with AgCN alcoholic, then there will be exchange to give R N triple bond C, which is known as the isocyanide. So cyanide can be obtained by the reaction with KCN, while isocyanide can be obtained by the reaction with AgCN. We can heat this with ammonia, provided the alcoholic ammonia you have taken and this particular ammonia has to be taken in excess. So if you take this in excess, then we get formation of corresponding primary amine. So it is simple. Byproduct is HX, NH2 is replacing that X. Why it is written that NH3 is there in the excess? Because if you use alkyl halide in excess, this primary will further turn to secondary amine, then tertiary amine and then quaternary amine. We can allow this to react with the magnesium in dry ether. We'll get formation of RMgX, which is nothing but Grignard reagent. We can allow this to react with sodium in dry ether. This will give you formation of higher alkane, which is known as the Wurtz reaction. Reaction with silver salt of carboxylic acid. There is a loss of AgX and we will get corresponding formation of esters. And finally, if you allow this to react with sodium alkoxide, then we'll get formation of corresponding ethers, which is known as Williamson synthesis. Now, overall, all these reactions, first of all, we need to focus on the reagents and what kind of products we are expecting. Now, in case of Williamson synthesis, the points to be remembered, when you are preparing certain ethers, if it is simple ether, the reaction becomes very easy. But when you go for a complex ether or a mixed ether, for example, if you want to go for formation of such kind of ether, let's say, we are preparing methyl tertiary butyl ether. The reactant for this reaction has to be the smaller alcohol and the larger alkyl halide. Or when we talk about this particular we are expected to get we are expected to get the formation of CH3OH or CH3CCH3 iodide, or we can take a combination like this, CH3CCH3. I'm taking alcohol of this and CH3I. Now generally it is expected the lone pair of oxygen attacks the other carbon. Now if you look at this particular attack, in this case this attack is very difficult because the lone pair is attacking the carbon which is already being crowded by the CH3. So here if I talk about this particular example where the lone pair is attacking the carbon which is least sterically crowded. So it is expected the larger alcohol and the smaller alkyl halide has to be taken for the reaction for the formation of the Williamson synthesis. Now in the next part there is one more method is to be involved in this all this reaction part. That is, if you allow this alkyl halide, for example RCH2CH2X, if you allow this to react with the KOH, but this has to be alcoholic. Here we have taken aqueous to get the alcohols. But if you take KOH which are alcoholic in nature, then we get formation of corresponding alkyl halide by the loss of H and X from this. Now if you are supposed to get two different kind of the alkyl halide or alkene during the reaction, for example let's say we have CH3 CH2 CH Br CH3. So if HX is lost from here, it may be lost from this carbon or it may be lost from this carbon. So if it is lost from this carbon, I'm expected to get 2-butene. And if it is lost from the terminal, I'm expected to get 1-butene. So in this case, we are expecting which major product is to be formed. That is to be decided according to the Setzeff rule. Now the Setzeff rule says that when the two different alkene are expected in the reaction, then the one which is more substituted is a major product. And hence 2 substituted alkene is the major product compared to the 1 alkene. Now let us focus on the reactions of the alkyl halides. In case of reactions of alkyl halide, in the case of preparation part, we'll focus on only one reaction, that is electrophilic substitution. We can start with simple benzene. Benzene on reaction, that is halogenation. This occurs in presence of Fe. Dark is important. This will give you formation of corresponding haloarenes. Now also we can start with aniline. The diazotization of aniline will give you the diazonium salt. And this particular diazonium salt can be converted into the corresponding alkyl halide by allowing with the reaction with the copper salt, that is your Sandmesh reaction. So two methods are possible, that is direct halogenation we can do in presence of catalyst, or we can start with aniline, convert it into diazonium salt and then convert into X by the Sandmesh reaction. Now different reactions related, that is all electrophilic substitution related to haloarenes, that can be summarized in this way. If I allow this to react with nitric acid, that is HNO3, nitric acid plus a mixture of H2SO4, so we call this as nitrating mixture, then there are two products are expected. One is ortho product and one is the para product. Out of this, the major one is a para product because of the steric crowding effect is minimized over here. We can carry out the sulfonation of that by allowing it to react with concentrated H2SO4. Again, sulfonation will give me two products, SO3H at ortho position or SO3H at the para position. Now here again the major product is the para one. Similarly, we have to remember all Friedel-Crafts reaction. If you allow this to react with CH3Cl, alkyl halide, let's say in general I'm talking about Rx, then there will be two products, either R will be introduced at ortho position or R will be introduced at the para position. major is always the para product. This is called a Friedrich graph alkylation. The same thing you can do it with the acyl halide also. So instead of alkyl group, there will be introduction of acyl group. Again, the major product in this case is the para product. Then we can allow this to react with or direct halogenation. Halogenation again will give you product at ortho or will get the product at the para. So overall, all this reaction you will find all electrophilic substitution for the haloarenes occurs at ortho and para position. That's indicating the haloarenes are ortho para directing and giving the para as a major product due to less steric crowding. One more concept that we are going to focus in this chapter, that is related to the SN1 and SN2, because most of the MCQs related to this are asked, that is comparative studies of the SN1 and SN2. Now in case of SN1 and SN2, how we can focus is, in case of SN1, it is always, remember, it is unimolecular and it is two-step reaction. When I'm talking about this is two-step reaction, in the first step there is formation of carbocation. This is the main focus point we have to focus while deciding whether the reactant will undergo the SN1 or not. While in case of the second one, it will be attacked by the corresponding nucleophile to give the final product. In case of SN2, it is a one-step reaction and this one step involves the backside attack. So these are the focus points we have to just understand. When I'm talking about the formation of carbocation, then we have to remember the order. In case of order, the benzylic is more stable, then allylic carbon atoms are more stable, then tertiary, then secondary, and then primary. For the backside attack, you have to remember the backside of the reactant has to be less crowded. Then only we can think about SN2 is possible. So for example, if we have a comparison, let's say we have CH3C, CH3Br and CH3Br. Now we have to decide which one is undergoing the SN1 nucleophilic substitution and which one is undergoing SN2 substitution. So in this case, how to decide or how to get the answer in this case is, if I talk about if the Br is lost in this case, let's imagine the Br is lost, I'll get a positive charge on this carbon. This particular carbon is attached to 3 carbon, that means I'm going to get the tertiary carbocation over here. While if this Br is lost from this, I'm going to get the primary. But if according to the formation of carbocation, if I'll find tertiary is more stable than the primary, so this can give us a more stable carbocation. So this is expected to give the SN1 mechanism and this is expected to give the SN2 mechanism. So we have discussed this with respect to formation of carbocation. So you can also discuss with respect to backside attack. Suppose the reagent is attacking this particular compound from the backside. Br is a front side. So backside, if it is attacking backside, we have already crowded with the 3-methyl group. So this is very difficult to attack from the backside. While this particular carbon can be easily achieved, hence again confirmation that it is having the SN2 mechanism to be confirmed with this. So while doing the MCQs related to this, we can focus on this SN1 and SN2 mechanism. Let us talk about different reactions and the methods of preparations of the alcohols, phenols and ethers. So MCQ point of view related to that will be focusing. First of all, let us talk about methods of preparation for alcohols. Now in case of alcohols, we can prepare this from different alkyl halides. So alkyl halides can be converted into alcohols by allowing it to react with aqueous KOH, or we can take aqueous AgOH. This is nothing but moist silver oxide. So the X nucleophile is being replaced by the OH to give corresponding OH. We can start with the alkenes also. But in case of alkenes, now depending on what condition you are using, here we are going to get the different products. Now in case of alkenes, what are the conditions which are acid catalyzed or the boron catalyzed reactions we are going to form, accordingly we are expected to get the different products. For example, if I talk about the alkenes, let's say RCH double bond CH2. Now if it is allowed to react with concentrated H2SO4, then this will give you the addition according to the Markovnikov's rule. So R OSO3H will be added to the carbon having less number of hydrogen atom, and this will become CH3, and the hydrolysis of that will give you formation of RCH OH CH3. So we are going to get the secondary alcohol with this reaction. The only alcohol, primary alcohol, which is possible by this method is only the ethanol, which is only possible. But suppose if I do the same reaction, RCH double bond CH2, and rather than acid catalyzed, if you go for some boron, B2H6, then we'll get RCH2 CH2 thrice B, triboron complex, and this particular trialkyl boron further on hydrolysis in presence of peroxide will give you formation of RCH2 CH2OH. That's we are going to get the primary alcohol. So from the alkene we are expected to get two different conditions. Acid catalyzed will most of the time gives you secondary, no primary possible, only primary is ethanol, and second is boron reaction, that will always give you formation of the primary alcohols. Then in case of reduction, we can obtain from aldehyde or we can obtain it from the ketone. So aldehyde, suppose if I start with R C double bond O H aldehyde, this is going to give me the formation of primary alcohols. If I start with ketone, I'm expected to get the secondary alcohol by this reaction. No tertiary is possible with this method. Okay, so by reduction we can obtain corresponding alcohols from the aldehyde and ketone. Aldehyde always gives you primary, and ketone always gives you the secondary. Now what are the reducing agent we can use over here? We can use mercury, sodium amalgam, we can use the ranitidine, that is nickel hydrogenation we can use. So these are the different conditions can be used. But suppose if I take this aldehyde and ketone and if I allow this to react with the Grignard reagent. So fourth method of preparation, that is from the Grignard reagent. This is the most important part, just focus on this. RC double bond OH. This is are of two types. First of all, if I start with HC double bond H or RC double bond H. So first condition is for formaldehyde, second condition for any aldehyde other than formaldehyde. So if I allow this to react with RMGX, I'm going to get the formation of primary alcohols. If there is a combination of other aldehyde other than formaldehyde with the Grignard reagent, we'll get a secondary. And if you use ketone over here, then we are expected to get the tertiary. So this particular chart to be remembered, because this is the way, in a shortcut way, we can solve the MCQs. Formaldehyde combination with Grignard reagent, primary. Other aldehyde with Grignard reagent, secondary alcohol. Ketone along with the Grignard reagent will always give you the formation of tertiary alcohol. So these are all methods of preparation of the alcohol that we need to focus for the MCQs. Now in case of reactions of alcohols, let us focus on this. We can convert this into alkyl halides. Now conversion to alkyl halide, we can do this by the different methods. We can use HX over here. If I allow the alcohol to react with HX, then we'll get corresponding alkyl halide. In case of HX, we can use HCl, we can use HBr, or we can use HI. HCl is the weaker one, need a catalyst ZnCl2 called as the Lucas reagent over here. In case of alcohols, reactivity over here, we have to remember tertiary is more reactive than secondary and then the primary alcohol. We can also use all PX3 over here. So ROH can react with PX3 so as to give corresponding RX with the byproduct H3PO3. In case of PX3, we have three options over here. We have PCl3, we have PBr3 and we have PI3. In case of, we can also go for PX5. So ROH plus PX5 will give you formation of RX plus POCl3 plus HCl. In case of PX5, we have only one option, PCl5. But the best option amongst this is using SOCl2. So we can go for ROH plus SOCl2 will give you corresponding alkyl chloride along with SO2 and HCl. So it's always the byproducts are gaseous in nature in this case, and that's why this reaction is giving us the major product, that is, as the byproducts are gaseous in nature, no purification required for the alkyl halides. We can allow these alcohols to react with the different olefins, concentrated H2SO4, so as to convert them into olefins. So we can convert them into the olefins, but again, depending on which type of alcohol we have, we need a different condition. So primary alcohol, secondary alcohol, tertiary. Primary alcohol, secondary and tertiary, amongst this, the primary is the least reactive one and hence need more concentration, around 95% of concentrated HNO3 and high temperature or about 443 Kelvin. This requires 60% of H2SO4 and around 373 Kelvin. And this require only 20% of H2SO4, so and around 363 Kelvin around temperature is required. So they will be all turning to corresponding olefins by reaction with the concentrated H2SO4. Instead of the concentrated H2SO4, you can also use the alumina as a reagent in this case. So temperature required always higher for the primary, then secondary, then tertiary to give you corresponding olefins. We can allow this particular alcohols to react with the sodium so as to get sodium alkoxide. And we can make this sodium alkoxide to react with RX so as to give corresponding ether. So ether formation can be done with the help of the alcohols. We can allow this to react with the carboxylic acid, which will give you formation of the esters. But the ester reaction like this is reversible in nature, which can be made, or the yield of the esters can be obtained by using a dehydrating agent, because the byproduct in this reaction is the water. But the main point, that again the next reaction that we are going to focus is the oxidation of alcohols. Now in case of oxidation of alcohols, we need to focus on certain things: primary, secondary, tertiary. Now in case of primary, if you oxidize this, first we'll get formation of aldehyde, which on further oxidation we give you formation of the carboxylic acid. So primary alcohol will give you first aldehyde, then acid. In case of the secondary alcohol, you get formation of ketone, but the further oxidation is very difficult. In case of tertiary, no oxidation or difficult to oxidation, we can say. So we can distinguish the primary, secondary and tertiary alcohols using the oxidation reaction. So these are the focus points that we have to remember. Mainly you need to focus on how to convert the alcohols into olefins and how to convert alcohols or their oxidations to get the corresponding carbonyl compounds. Let us talk about next part, that is phenols. Now we are going to talk about how to prepare the phenols. Now phenols can be prepared by the different processes, by the different compounds. Let us first talk about phenols can be prepared from the chlorobenzene. Now if we need to prepare phenols from the chlorobenzene, we have two different options. We have Raschig's process, where this particular chlorobenzene is allowed to react with the superheated steam in presence of the calcium phosphate as a catalyst at around 698 Kelvin, where the direct replacement of the Cl by the OH will give you the corresponding phenol. Or we can go by the Dow's process, in which we heat it or fuse it with the NaOH at around 300 atmospheric pressure and around 623 Kelvin, which gives us formation of the sodium phenoxide, and this is on further acidification with the acid like HCl gives you corresponding phenol. So two different processes from the chlorobenzene, either Rashing process or the Dow's process. We can also prepare this from benzene sulfonic acid, that is SO3H. First fusion with the NaOH. It will be simple neutralization reaction to give the sodium salt of the sodium sulfonic acid. This is further on reaction with NaOH, that is on heating, will give you formation of the sodium phenoxide. And that is, you can again acidify with different acids. Here we have used HCl, you can use H2SO4 in this case, so as to get formation of the phenol. We can also prepare this from cumene. Cumene is isopropyl benzene. Now this isopropyl benzene, first on oxidation, air oxidation, will give you formation of cumene hydroperoxide. So this is COOH CH3 CH3. So this is cumene hydroperoxide which is formed, which is on acidification will give you corresponding phenol. This is called as a commercial method of preparation of phenol, because here the byproduct formed is acetone, which is equally commercially important one. We can also prepare the phenol from aniline by doing diazotization of this, by allowing it to react with NaNO2 and HCl. So this will give you first formation of the diazonium salt, which is on hydrolysis further gives you formation of the phenol. So four methods of preparation we do have to remember: from chlorobenzene, benzene sulfonyl chloride, cumene, commercial method, and the aniline. Now related to the reactions of the phenol, we have a different type of reaction: electrophilic substitution as well as the nucleophilic substitution type of reaction. First of all, depending on the conditions which you are using, the product will differ here. Now here if we use concentrated H2SO4, now if you allow this to react with concentrated H2SO4, there will be two different conditions. If you use room temperature, the reaction will specifically occur at the ortho position. And if you carry out this around 373 Kelvin, that is under boiling condition, you are expected to get the para product. Now if you carry out the bromination of this, can be done in two different solvents, either bromine water or in presence of CS2. Now if you use the bromine water, which is very strong reagent, which will give you the bromination at ortho as well as para position. So we are expected to get 2,4,6-tribromophenol. But if you carry out in presence of CS2, then we'll get ortho plus we'll get a para product. But out of this, the major product is the para product due to the less steric crowding. We can carry out the nitration of this concentrated HNO3 plus H2SO4 as a mixture. Now in this, remember, I'm just omitting the word concentrated. I'm using the acid mixture. If this is concentrated, then this is a strong reagent which will give you nitration at all three positions. We get 2,4,6-trinitrophenol, which is commonly called as picric acid. But if you use a dilute condition over here and room temperature, then you are expected to get two products, ortho product and the para product. But here, to be remembered, the major product is the ortho product. This is because here we have two groups, that is OH and NH2, which is kind of like a hydrogen bonding, intramolecular hydrogen bonding, which will stabilize the product. That's why ortho product is a major product compared to the para product in this case. We can carry out the reaction. We can allow this to react with the NaOH. that will carry out a neutralization to give the formation of sodium phenoxide, and this further on the reaction with the CO2 H plus will give you introduction of COOH group at ortho position. Also, if you carry out this reaction with chloroform NaOH, then this will give you introduction of CHO group, followed by the acidification will introduce the CHO group at the ortho position. So salicylaldehyde and salicylic acid. Salicylic acid can be prepared by reaction with CO2 and followed by the hydrolysis, while the aldehyde can be prepared by reaction with chloroform. Finally, two important reaction. One is a reaction with the zinc, will give you formation of benzene, and one is oxidation with a reagent like Na2Cr2O7 in acidic media like H2SO4 will give you formation of benzoquinone. So reduction of phenol with the zinc will give you benzene, and oxidation of phenol with the sodium this dichromate will give you formation of benzoquinone. Now, in the third part of this particular chapter, we are going to discuss about the ethers. Now, ethers can be prepared by three different methods. We can start with alcohols, but we need a symmetrical or a single alcohol over here. So, two molecules of alcohols in presence of concentrated H2SO4 will give you formation of corresponding ether. Only the symmetrical ether are possible by this method. That is to be remembered. Another thing is this particular reaction involves the attack of the oxygen lone pair on the other alkyl group, and hence the other alkyl group which is participating in this reaction should be less crowded. Hence this particular reaction is only valid for the primary alcohols, not for the secondary, not for the tertiary, as they are more crowded for the backside attack, that is SN2 mechanism followed in this reaction. So no reaction for the secondary and tertiary. As I said, this is only possible for the symmetrical, because if I have to make the unsymmetrical ethers, I have to take a combination of two different alcohols, and that will give me the combination of three different type of ethers, mixture of three ethers. So that is to be avoided. We can also prepare this by reaction of sodium alkoxide with the alkyl halide to give formation of the ether, which is called as Williamson synthesis. In Williamson synthesis, that we have to always remember, the lone pair of this attacks this smaller R group of the alkyl halide. So alkyl halide has to be less crowded and this has to be larger one. So group, while selecting the mixed ether formation, select the options accordingly. There has to be smaller alkyl halide and larger alkoxide. And third method is reaction of alcohol with diazomethane in presence of hydrogen fluoroborate, so as to give formation of methyl ether. This method is specifically used for the formation of the methyl ethers. Talk about now the reactions of ether that we need to focus. Now, if you are talking about reaction of ether with HI, that will occur under two conditions. One is a cold condition and one is a hot condition. In the cold condition, there is always formation of alkyl halide and one alcohol. Always remember, there is always formation of smaller alkyl halide and larger alcohol, provided your R and R dash groups are primary and secondary. But if your R and R dash groups are tertiary, then the tertiary forms the halide. That thing you have to remember. The other group, whatever it is, that will form the alcohol, but the tertiary group will always form the halide. For example, let's say we have CH3, O, CH3. If I allow this to react with HI under cold condition, then I'll get formation of CH3 iodide plus CH3OH. Under hot condition, both of them are going to form the alkyl halide. So there is no rule for this, as they both are forming the alkyl halides. In case of the reaction with the concentrated H2SO4, here you are going to get both the molecules will form the corresponding alcohols. One more thing that is to be remembered, in case of the aromatic ethers, aromatic ether is ortho-para directing. All the reactions, whatever you condition you do, all the reactions will occur at ortho as well as para. But the major product is always the para product because of the less steric crowding. So all electrophilic substitution for the aromatic ethers will occur at the para position. In the next part, we are going to talk about the different reactions and the methods of preparation for the aldehyde, ketone and the carboxylic acid. Let us have a comparison study for the preparation of the aldehydes and the ketone. Now, if you start with the starting material, let's say RMgX, that is Grignard reagent. If you want aldehyde, the Grignard reagent is to be allowed to react with HCl, hydrogen cyanide. Hydrogen cyanide reaction with the Grignard reagent will give you corresponding aldehyde formation. But in the case, if you allow this RMgX to react with any alkyl halide, alkyl cyanide, this hydrolysis will give you formation of corresponding ketone. So Grignard reagent with HCl aldehyde and Grignard reagent with alkyl cyanide will give you formation of ketone. We can prepare this from the alcohols, but here we need primary alcohol. Now primary alcohol can be converted into the alcohols by can be converted into aldehydes by the oxidation. But remember, we cannot use the strong oxidizing agents like K2Cr2O7 or chromic acid, because that will not stop the reaction at aldehydic stage. So we need reagents like PCC or PDC. Their milder oxidizing agent will convert the corresponding primary alcohols into corresponding aldehyde. But to get the ketone from the alcohols, here we need secondary alcohol. Here any kind of the oxidizing agent will do, which will oxidize it to corresponding ketone. We can prepare this from the halides, but we need the dihalides. Now here, if you have to prepare the aldehyde which has to be taken has to be geminal. Geminal dihalide we can start, but the geminal dihalide has to be terminal. So in the case, suppose we have a terminal geminal dihalides like this. This will undergo hydrolysis, let's say with aqueous KOH, where both this X being replaced by OH, which is unstable compound, loses water molecule to give the aldehyde. But we can prepare this from non-terminal geminal dihalide. So non-terminal geminal dihalides will be like this, which will give you diol compound, which is also non-terminal, unstable, will give you formation of ketone. We can prepare this from the carboxylic acids, but in case of carboxylic acid we have to make a salt, and generally we are going to take the salt which has to be the calcium salt. Now in the case of this, if you take any calcium format, let's say calcium salt, HC double bond O, HC double bond O, Ca. If you just heat it, you will get corresponding formaldehyde formation here. But if you take combination of any calcium format, this format, plus any calcium salt of other acid, then you will get specifically formation of the aldehyde. But here if you want to prepare this from the carboxylic acid, then you have to take other than formaldehyde. So you need calcium carboxylate but not formate. If you take any format in this case, definitely one of the group will be H, and that will give you formation of the corresponding aldehyde, not the ketone. So here if I take, let's say R C double bond O Ca, R C double bond O Ca, plus one more R dash C double bond O Ca, R dash C double bond O Ca, that will give you formation of this with the loss of calcium carbonate. We can also prepare this from the alkyl cyanides. Alkyl cyanides will only give you formation of the aldehyde. Here alkyl cyanide we have used along with a combination of the Grignard reagent, but we can also use only alkyl cyanide, which is on reduction with stannous chloride will give you formation of, followed by the hydrolysis dilute HCl, will give you formation of only aldehyde. Now from alkene we can prepare aldehyde and ketone, but if you are having the one alkene having at least one hydrogen with the carbon containing the double bond, then this will give you formation of aldehyde by ozonolysis. Because in ozonolysis what happens, if the ozone is added, so we get R, C, H, O, C, H, R. So ozonide complex, which will break at both the side and will give you two molecules of the RH. But if I want ketone from the alkene, there should not be any kind of H on the carbon containing double bond. So this on ozonolysis will give you formation of the ketone. We can also prepare this from the alkyne. From alkyne we just to remember, if I take acetylene, this is the only compound which give you aldehyde by reaction with concentrated H2SO4, but this will give you formation of aldehyde, which is acetaldehyde. That's the only aldehyde possible from the alkene. But for ketone we have variety possible with other than acetylene. All acetylene, alkyl derivatives of acetylene will give you formation of the ketone by reaction with concentrated H2SO4. So all these are the summarized or the comparative study of the reaction, because that is more important when we have a comparison study for the reaction for aldehyde and ketone while solving the MCQs. Similarly, let us focus on the comparatively study for the reactions also. So let us talk about RCHO reactions compared with RC double bond R dash reaction. Let us talk about first its reaction with HCl. There will be simple addition reaction. R, C, H, O will get H and carbon will get the cyanide. Because in this case the structure is like R, C double bond O, H. This is partially positive, negative. Between HCl, hydrogen is positive, cyanide is negative. So cyanide goes to the carbon and hydrogen gets to the oxygen. Similarly here also there is a simple addition to get the corresponding cyanohydrine. So R dash OH Cl. If you allow this to react with sodium hydrogen sulfide, then similar addition RCH, this will become OH and this is addition of SO3Na. So sodium bisulfide salt are formed. Similar reaction you will get it here, RCR dash OH SO3Na. So far we can see there is no difference in the reactivity of aldehyde and ketone. If you allow this to react with ammonia, again there is a simple addition, will give you R, C, OH, NH2H. Here there is a difference. Now when I'm talking about the aldehyde, when you're talking about this reaction is only possible for other than formaldehyde. If this reaction occurs for formaldehyde, we have to remember we get the formation of urotropine as a product. Urotropine is a hexamethylene tetraamine complex. So urotropine is formed during the reaction of ammonia with formaldehyde. Acetaldehyde will give you simple addition of product which undergoes the trimerization, which is acetal will be formed in this reaction. Here reaction with ammonia will give you the complex first, will give you diacetone amine. So CH3, CCH3, NH2, CH2, C double bond O, CH3. Now how this is formed? First reaction will carry out, or this instead of this R, I have written here R, so here CH3 has to be there. For example, CH3, C double bond O, CH3 if I am using, that will undergo first loss of water molecule like this, CH2. This is CH2 is, that is H is lost from here, that is CH2. It is going to create a double bond here and then followed by C, followed by CH3 and CH3, where the ammonia will be added here. So NH2 will come here and H will come here. That is going to give you this product. So reaction with ammonia is different in the case of aldehyde and the ketone. Reaction with the RMGX, we have to remember, if we are using formaldehyde, then you'll get a formation of primary alcohol. And if you are using other aldehyde, I'm going to get formation of the secondary alcohol. In case of ketone, RMGX will give you always formation of tertiary alcohol. So these things to be remembered while doing the MCQ solving for related to the Grignard reagent. Now in case of next part, reaction with alcohols in presence of the HCl gas, this will give you kettle formation. So R, Cr dash, OR, OR. Similarly, acetyl formation with HCl. So R, CH, OR, OR. So acetyl formation here and kettle formation here. Now in the case of the next part, we are going to talk about its reduction reaction. Aldehyde, when it is reduced, let's say with the help of sodium amalgam or with the help of ranitidine nickel, will give you formation of primary alcohol. While this is on reduction with the sodium amalgam and ranitidine nickel, will give you formation of the secondary alcohol. In case of reaction of this with the Wolff-Kishner reaction, that is hydrazine, will give you corresponding alkene. Here also you are going to get the formation of the corresponding alkene only, but here this will be containing one extra carbon. So you can write it as R, CH2, R dash. So Wolff-Kishner reduction will give you corresponding alkene. Here also one more reduction. If you allow this to react with primary amine, then you will get R, primary amines R and H2. There will be simple condensation reaction. So R, CH, double bond, NH, R. Here also simple condensation reaction R, C, R dash, double bond, N, R. So all these are condensation reactions which are possible with respect to the amine. Now for overall all other reactions, simple condensation reactions, just remember, you take aldehyde or you take ketone. These reactions are common for them. You allow it to react with hydroxyl amine, there will be simple condensation to give oxime. If it is ketone, you will get RC, R dash. So instead of hydrogen, there will be R dash to give corresponding oxime. You can allow this to react with hydrazine, then you will get corresponding hydrazone. You can allow this to react with phenylhydrazine, then you will get corresponding phenylhydrazone. You can allow this to react with 2,4 DNP. I'll get corresponding, that is dinitrophenylhydrazine. So I'll get corresponding dinitrophenylhydrazine. So all these are condensation reactions which are possible. Okay. Here we have to also focus on the main important reaction, that's aldol reaction and the Cannizzaro reaction. Aldol reaction, if I'm talking about aldehyde, in presence of alkali, strong alkali, let's say we are doing this aldol condensation with let's say R is CH3CHO plus CH3CHO, then one of the carbon will lose oxygen, while the second carbonyl carbon will lose oxygen, while here the alpha carbon will lose the hydrogen, H2 is lost, and you will get this product. So it's aldol product, that is after the water loss. Also remember, this particular reaction is also possible for ketone. Now if in case of ketone, let's say we have this, while writing the final product for the aldol with the loss of water molecule. Always remember you have to remove oxygen from here and from the alpha carbon H2. So product is CH3, C, CH3, double bond here. This will lose H2, so CH is left, C double bond O, CH3. Same reaction if you carry out in presence of the strong alkali. This is carried out in presence of weak alkali. If we carry out in presence of strong alkali with the compound like HCHO or benzaldehyde, that is the one which is not having the alpha carbon. Aldol is only possible for those which are having alpha hydrogen atom. Here the alpha hydrogen is not there, so this kind of product on reaction with alkali gives you formation of one alcohol and one that is acid. So here suppose we are carrying out this reaction in presence of 50% of NaOH. This is expected to give one acid component, sodium salt of acid, plus we are going to get formation of one alcohol. So one molecule of formaldehyde is reduced to alcohol and one molecule is oxidized to acid. It's known as the Cannizzaro reaction. Now let us talk about the different reaction of the aromatic aldehyde. In case of aromatic aldehyde, how to prepare this aromatic aldehyde? First, we can prepare it from the benzene by reaction with carbon monoxide and HCl in presence of AlCl3 and copper chloride. This will give you formation of the corresponding aromatic aldehyde. We can also prepare this from the toluene by using reagents like chromyl chloride, or we can use the acetic anhydride. So this kind of reagent will give you formation of the aromatic aldehyde. We can also use the Rosenmund reduction COCl on reaction with palladium supported on BaSO4 reduction to give corresponding aldehyde. So three methods of preparation for the aromatic aldehyde can be used in this reaction. That is, first we can start with benzene, we can start with the toluene, or we can start with the carbonyl compounds like benzoyl chloride. We can convert this into the corresponding aldehyde by the Rosenmund reaction. Now reaction related to this, all reactions which are whatever we have studied for the aldehydes, they are all reactions possible for this. Only the thing, the separate reaction we have to study if you carry out a nitration of this with nitrating agent like mixture of HNO3 and H2SO4. Always remember aldehyde group is a meta-directing. So this will carry out the reaction specifically at the meta position. Now in case of aldehyde and ketone, we need to focus on certain test reaction. First of all, we are going to talk about the Tollens reagent. In case of Tollens reagent test, this is a reaction of corresponding aldehyde with the Tollens reagent. Tollens reagent is ammoniacal silver hydroxide. So this can be used for the reaction so as to convert the aldehyde to corresponding acid. And while this is undergoing the reduction so as to give the silver, so this silver is deposited on the surface of the mirror, giving the silver mirror test. This test is only possible for the aldehyde. We can also carry out Schiff's reagent test. In the Schiff reagent also, the aldehyde is treated with para-rosanilene hydrochloride, where we are expected to get the pink color. That is because of the reduction of the reagent and oxidation of the aldehyde to acid. Or we can go for the Fehling solution, where the Fehling solution, it's the copper 2+ solution in presence of hydroxide. This is oxidized to corresponding acid, while copper itself undergoes reduction to form Cu2O, which is a red precipitate. So all these three tests you need to revise while doing the MCQs related to the aldehydic test. One of the important reaction we need to focus on aldehyde ketone while solving this is the haloform reaction. Now in case of haloform reaction is only possible for those aldehyde and ketone having at least one CH3 group besides the carbonyl. Okay, this is a reaction of ketone compounds with the sodium halide, hypohalide, that is prepared by reaction of NaOH with halogen. So that will give you formation of corresponding salt along with the haloform. So haloform reactions are only possible for the carbonyl compounds having one at least CH3 group, and that's why for aldehyde, you remember, that's only possible for acetaldehyde. Other derivatives of ketone possible, but remember the ketone which are having CH3 at least on one side will give you haloform test. Most of the time you will deal with the reactions, haloform reactions, where they will ask you which of the following compound can give you this reaction. So remember, they may give you in the option alcohols also. So you just remember alcohols to be converted into aldehyde. For example, if they give you this, or CH3 CH2 OH, and if they ask you which of the following is can give you haloform test. So now we have to remember that if I oxidize this, I'll get formation of formaldehyde. Formaldehyde is not having CH3 besides the C double bond O, so this will not give you haloform. This will give me formation of acetaldehyde having CH3, so this will give me haloform test. When this is oxidized, this will give me formation of the ketone acetone, which is having CH3, so this is also going to give me the haloform test. So haloform test is to be remembered, there has to be at least one CH3 besides the carbonyl group. In the next part, we are going to talk about the formation of RCOOH and their methods of reactions. We can prepare RCOOH from cyanide by hydrolysis reaction, where first we get formation of corresponding amide, which is on further hydrolysis will give you acid. So remember, cyanide can be converted into COH by the hydrolysis. We can prepare it from Grignard reagent by reaction with dry ice, which gives us first the magnesium intermediate complex, which on hydrolysis gives us the formation of the carboxylic acid. We can also prepare this from primary alcohol, which on oxidation first gives us formation of aldehyde, which further oxidation gives us formation of the acid. So these are three methods of preparation we need to focus while doing the methods of preparation for the carboxylic acid. Now the different reactions of carboxylic acid, if you allow this to react with ROH, you will get formation of corresponding esters. You need to use dehydrating agents like concentrated H2SO4 in this reaction. We can allow this to react with P2O5, which will carry out dehydration of two molecules so as to generate anhydride of the corresponding acid. We can allow this to react with ammonia, which will first give us formation of ammonium salt, which is on heating will give us formation of corresponding amide. We can allow this to react with SOCl2, where OH will be replaced by Cl to give corresponding acid chloride. We can carry out the direct reduction with lithium aluminium hydride to convert this into corresponding primary alcohol. And finally, this reaction is only possible for the one which is having the alpha carbon atom. So this is a reaction with the red phosphorus and halogen. This is called as Hell-Vollard-Zelinsky reaction, which gives you formation of alpha halogenated carboxylic acid. So these are all reactions of the carboxylic acid and the method of preparation that you need to focus on. Let us talk about now important reactions of compounds containing the nitrogen. First of all, we'll be focusing on the methods of preparation of the primary amines. Now here we can prepare the primary amines from the alkyl halides. This method is known as Gabriel's thalamide synthesis, where we need a thalamide on reaction with KOH, alcoholic KOH, which will form a salt. This salt further on reaction with the alkyl halide will give you formation of the alkyl derivative of phthalimide that finally hydrolyzes to give corresponding primary amine. This particular method, we have to remember, is not applicable for the aryl halide, because this kind of cleavage for the aryl halide, it's not possible. That is, nucleophilic substitution is not possible for the aryl halide. We can do the ammonolysis, alkyl halide reaction with the ammonia. Remember, this has to be excess, will give you formation of corresponding primary amine. Remember, we need excess of ammonia in this reaction, because if you carry out this particular reaction in presence of excess of the alkyl halide, that may give you formation of different byproducts like primary amine, secondary amine, or tertiary amine, or the quaternary amine. Then in case of the next part, that is, we can carry out the reduction of the different compounds. Here first we can start with the oximes. In case of oximes, aldoxime on reduction with the sodium ethanol will give you primary amine. Even the ketoxime will give you formation of the primary amine only. Alkyl cyanides on reduction will give you formation of the primary amine. Amide on reduction will give you formation of the primary amine. Here point to be remembered for the amide, that this will give you the amine containing the same number of carbon atom. But suppose if I start with the amide and if I allow it to react with the bromine and NaOH, called as Hofmann's bromamide degradation, this will reduce one of the carbon atoms. So you will get the amine here containing one carbon atom less compared to the amide. We can prepare it from the nitro compounds by the reduction, but very strong reducing agent required here, tin HCl, that will reduce it to corresponding primary amine. So these are a summary form of the all methods of preparations of the primary amine. Now, while discussing the reactions, we are going to have a comparative study for the primary, secondary and tertiary amine. Let us talk about primary amine, first reaction, that is Hofmann's carbylamine test. The reaction with chloroform and KOH. If you allow this reaction with the chloroform and KOH, the primary amine turns to the RNC, that is isocyanide, which is having the foul odor. So characteristic test of the primary amine. In the MCQ, they can ask you amine which is on reaction with the chloroform and KOH gives you a foul odor. So you can mainly focus, say this is primary amine, because that gives you formation of isocyanide. If you talk about the same reaction with the Hofmann's reaction with the secondary amine, there will be no reaction. If you talk about the same reaction with the tertiary amine, there will be no reaction. So in short, the carbylamine test is not possible with the secondary and tertiary. It's only possible for the primary amines. Now in case of Hinsberg test, that's reaction with the aryl sulfonyl chloride, there is a loss of HCl and you'll get a salt of this. Now with reaction with the primary amine, with the loss of this HCl, still there is one hydrogen left on the nitrogen. This hydrogen is acidic in nature because it is having the electron withdrawing group sidewise. Since this is acidic compound, this will be solubilized in KOH. You'll get a similar reaction with the secondary amine also. But the thing is, this is not having any acidic nitrogen on the secondary amine. Hence, this particular compound will be insoluble in KOH. While the same reaction, there will be no reaction, Hinsberg test, for the tertiary amine. In case of next, one of the important point to be remembered, that reaction with the nitrous acid. Nitrous acid is a reaction, or it's a combination of NaNO2 and HCl. Primary amine gives you formation of alcohol with the liberation of one inert gas, that is nitrogen. Same reaction with the secondary amine will give you N-nitrosoamine, which is yellow oily liquid. And with tertiary amine, you will get a trialkyl ammonium nitrite, which is water soluble compound, hence no visible change for the tertiary amine. Next, Hofmann's exhaustive alkylation. That means go on doing alkylation till all the valencies of the nitrogens are satisfied. So primary will turn to secondary, secondary will turn to tertiary, tertiary will turn to quaternary. So this consumes around 3 moles of alkyl halide. But same reaction, if you talk about the secondary will turn to tertiary and quaternary, hence it consumes 2 moles of alkyl halide. While here, there is only one step, so consumes only 1 mole of alkyl halide. In case of acylation of the amines, in acylation, this is having, the NH is having 2 hydrogen, so mono and di, both acylations are possible. Here only monoacylation is possible in case of secondary, while the no acylation reaction in case of the tertiary amines. So all these are summary form of the reactions for the primary, secondary and the tertiary amine. Now here we are going to focus on one more reaction, that is of the quaternary amine, important reaction in MCQ point of view. In case of quaternary amine, quaternary salt, let's say this, is allowed to react with the silver hydroxide. The iodide being replaced by the OH, so instead of iodide salt, we'll get the formation of the hydroxide salt. If you heat it with the it will heat it at this particular compound at higher temperature. Then one of the alkyl group undergoes the elimination reaction to give corresponding alkene. In this reaction, we have to remember that beta elimination will always give the formation of the least substituted alkane. For example, if you have the quaternary compound like this, let's say we have here propyl group and CH3 and CH3. Now the out of 4, methyl won't form the alkene, ethyl will form the ethene and propyl will form the propene. So we are expecting 2 different products after the elimination. But ethene is the least substituted and hence the major product will be ethene, not the propene for the product. So for MCQ point of view, just remember quaternary ammonium hydroxide on strong heating undergoes the beta elimination to give least substituted alkene. Now we are going to talk about some aromatic substitution reactions of the amine. This is important compound of the amine, aniline. If you carry out the bromination of the aniline, then the bromination can take place at all 3 positions. Now this can be avoided by protection of this NH2 group by the acetylation. So when you protect the NH2 group by the acetylation, we'll get acetanilide. After acetanilide, if you do this particular bromination, then bromination specifically occurs at the para position because ortho positions are being crowded with the help of this acetanilide group. If you do the hydrolysis of this CH3OH, CH3CO, that acyl group can be removed. So specifically the para product we can get only by the protection of the NH2 group. If you do the direct bromination, you will get a tri-bromo substituted compound. Similarly, if you do the direct nitration of the aniline, we are expected to get the 3 products. Now how 3 products? Aniline is ortho, that is NH2 is ortho and para-directing. So we are expecting ortho and para-directing. But one more thing is that aniline is a basic compound and this is acidic media. So in acidic media, this basic compound will form a salt, that's hydrochloride salt. And this hydrochloride salt is a meta-directing and hence we are also expected to get the nitration at the meta position. But we can avoid all the mixture of 3 products by protecting the NH2 group and then followed by the nitration to get exclusively the para product. While doing the sulfonation, you don't have to carry out such kind of protection because concentrated H2SO4 will protect the NH2 group by forming a salt. If you allow one more molecule of H2SO4 to react, the sulfonation specifically occurs at the para position. Now here we have NH2 group which is basic in nature and SO3H group which is acidic in nature. So this particular ion can exist as a Zweiter ion having the positive as well as the negative charge because it's bearing the basic and acidic group both. The next chart is very important with respect to the MCQs. This is a disonium salt methods of preparation as well as reaction. Now in case of methods of preparation, there is only one reaction. Aniline on reaction with NaNO2 and HCl at 0 degrees Celsius will give you formation of disonium salt. Now all these disonium salts can be converted to corresponding halides by 2 different reactions. One is Sandmeier's reaction where we can allow the disonium salt with a copper chloride to get corresponding chlorobenzene. Copper bromide to bromobenzene, copper cyanide to cyanobenzene. We can also carry out the Gattermann reaction. Rather than taking a copper salt, we can take a copper with the HCl to get chlorobenzene and bromobenzene. See here, cyanobenzene is not possible by this method. So if I'm going exclusively for the cyanobenzene, I have to go for the Sandwich reaction. Next part is you can prepare the fluorobenzene by this method. Diazonium salt is allowed to react with the hydrofluoroboric acid. This on heating will give you fluorobenzene, but if you allow this to react with NaNO2 during heating, it will give you corresponding nitrobenzene. Next part is we can allow this to react with simple aniline, one more aniline. So this will give you the para substitution, that's para to this position, para to the aniline, and this will give you formation of the diazo salt. So this azo benzene salt is kind of like a dye. So this is azo coupling reaction. We can carry out the same reaction with the phenol also in presence of OH minus will give you orange dye. Important with respect to MCQ point of view, because they give you generally this question, the diazonium salt on reaction with phenol in alkaline media. So we get the formation of orange dye and the yellow dye. In case of reaction of diazonium salt with the dilute sulfuric acid, that simple hydrolysis will give you phenol. Reaction with the ethanol or phosphoric acid, which is acting like the reducing agents, will reduce this corresponding benzene. Finally, heat it with the Ki to corresponding iodobenzene. So all these are important reactions of the diazonium salt. In the next part, we'll be talking about the different reactions or methods of preparation for the nitro compounds. In this case, we can carry out the nitration of the alkanes by heating it with the HNO3 under vapor phase. This is vapor phase nitration. We'll get the corresponding nitro compounds. But we have to remember that this reaction is only possible for the compounds like ethane. Methane it's not applicable. But if you carry it for the higher alkanes, you are expected to get the mixture of the nitroalkanes. So this is a very less popular method for the preparation of the nitroalkanes. We can also prepare this from the alkyl halide by reaction of the alkyl halide with the AgNO3 or NaNO3. So there is simple nucleophilic substitution so as to give the corresponding nitroalkanes. This can be also carried out with alpha halogenocarboxylic acid. This will be NaNO2 reaction. There will be loss of the NaCl followed by the hydrolysis to give the corresponding nitroalkanes. Also can be prepared from the alpha halogenoalkanes, where it will give you formation of the nitroalkanes by the hydrolysis reaction. We can also prepare them from the oxymes. We have aldoxime or we have ketoxime. Aldoxime on the oxidation using trifluoroperoxyacetic acid will give for a formation of primary nitroalkane, and ketoxime on oxidation will give you formation of secondary nitroalkane. We can also prepare them from the primary amines by simple oxidation so as to give corresponding tertiary nitroalkane. Now the way we did, we have revised all reactions of the primary amine. We are going to have a comparison study for the nitroalkanes as well. So we are going to compare the study of primary, secondary and tertiary nitroalkane. Now let us focus on the primary. Now this is primary nitroalkane. If I allow this to react with HNO2, in this what will happen? The NO2, that is NO, this is something I am writing HONO, HNO2. So this NO group will attack here. This will replace the hydrogen of this, and this hydrogen and this OH will form a water byproduct. So NO will be introduced here. Now here, after forming this nitroform also, there is still one hydrogen. And this hydrogen can undergo the tautomerism, that it will be shifted here and this double bond will be shifted here, so as to form the ACE form, which is a blue colored solution. This is an acidic form, and this acidic form on reaction with the base will give you formation of corresponding red solution because it's a salt solution. Now same reaction, if you talk about the secondary nitroalkane, you will get the substitution at this position, so you will get a NO. But now this carbon is not having any hydrogen, so ACE form of this is not possible. Since ACE form is not possible, you won't get a red color solution in the NaOH. Similarly, for the tertiary, there is no hydrogen only at this carbon, so there is no reaction with the nitrous acid. In case of reaction with the halogen, it's a haloform type of reaction. Here there are two hydrogens. So this both hydrogen can be replaced with the halogen. So you will get dihalogen derivative. If you carry out this reaction with the nitromethane, you're going to get the trichloronitromethane. So it's a chloropicrin, one of the important commercially compound. Here we have only one hydrogen, so only monohalogen derivative is possible with the halogenation. No hydrogen in this case, so no halogenation reaction. Next reaction with the aldehyde. Aldehyde will give you simple condensation reaction where it is kind of like a aldol condensation. Now here this will lose the hydrogen and this hydrogen will be transferred to carbonyl. So carbonyl carbon over here, it will become OH and this CH2 is going to become CH. So carbon-carbon bond formation will take place. This can lose for the water molecule so as to give the corresponding nitroalkenes. Similar condensation is possible for the secondary also because here we have one hydrogen. But now we don't have hydrogen on this carbon, because of this no further condensation possible. While no condensation reaction with aldehyde and ketone since no alpha hydrogen atom for the tertiary nitroalkane. In case of hydrolysis, the primary nitroalkane gives you corresponding carboxylic acid. Secondary nitroalkane gives you formation of corresponding ketone, while there is no reaction with the tertiary. When you carry out the reduction, primary nitroalkane will give you formation of primary amine, while the secondary will give you formation of primary amine only. Tertiary will give you primary amine. So here all nitroalkanes on the reduction are going to give you formation of primary amine. Reduction with the zinc in ammonium chloride. This is very important in MCQ point of view. Ammonium chloride, this is a milder reagent and it's giving you not amine, it's giving you hydroxylamine. Here also secondary giving hydroxylamine and tertiary also giving you hydroxylamine. Finally, the Nef carbonyl synthesis, one of the important reaction here. This is the nitroform, shifting of hydrogen to the nitrogen oxygen. This is a C form of the nitronic acid. This can be treated with the NaOH, so it will form a corresponding sodium salt. On dissolution or reaction with 50% H2SO4 will give you formation of aldehyde. Similar reaction when you carry out with the secondary will give you formation of the ketone. Well, this kind of aciform is not possible for the tertiary, so no reaction. So here overall we have revised all the reactions of primary nitroalkane, secondary nitroalkane and tertiary nitroalkane. So students, this is a quick revision of the solid state chapter. So let's talk about first the classification of solids. Depending on the presence or the absence of the orderly arrangement of the constituent particles, the solids are classified into two types, that is crystalline and the amorphous one. Now, in case of crystalline solids, we know that depending on what are the constituent particles, we classify them into four types. It is including of molecular solid, where the constituent particles are molecules of the same compound. Now, in case of molecule, which type of molecules you have, you'll classify them into three different types containing polar, non-polar or hydrogen bonded molecule. For example, when I'm talking about the polar molecules, these are consisting of the polar molecules like let's say HCl, or it will be containing like SO2, which will be having dipole-dipole interaction between each other. In case of non-polar solids, you will have non-polar molecules like CO2, it can be H2, it can be Cl2, etc. They will be having van der Waals forces between them. While in case of hydrogen bonded, the condition is the molecule should contain the hydrogen and that hydrogen should be either attached to the fluorine or oxygen or the nitrogen, which are the three most electronegative element of the periodic table. For example, molecules like water, we can say ammonia, we can say, or we can say HF. So these are the classification of molecular solids. We have to just remember for the MCQ point of view, all molecular solids are low melting and do not conduct electricity. The lowest melting amongst all of them is the non-polar molecular solid. Now, in case of the ionic solids, we have the solids which are consisting of the ions. So, it's consisting of the positively charged ions and the negatively charged ions. The force of attraction between the positive and the negative charged ions, obviously, it's electrostatic force of attraction. For example, like NaCl, or LiF. These are all examples of the ionic solids. They are hard but brittle. They are insulator in the solid state. But in molten state or in the aqueous state, they are good conductor of electricity and they are having high melting point. In case of metallic solids, they are consisting of positively charged metal cations which are embedded in a stream of the electrons. So the force of attraction between them is nothing but the metallic bond. So obviously they are metals, so they have high melting point, good conductor of electricity in solid state as well as in molten state. They are malleable, ductile and have the luscious shining. In case of the covalent solids, they are the solid where they are consisting of the most of the time non-metallic atoms. The force of attraction between the covalent bond. For example, different allotropes of the carbon, including the diamond, we can say, then graphite we can say, or we can talk about the fullerene. So these are all examples of the covalent solids. Now in the next part, we'll be talking about some important terms. First of all, if you have a three-dimensional arrangement of the atoms in the space, this entire three-dimensional arrangement, we call it as crystal lattice. Now, in this particular crystal lattice, if I look at this, it's actually a repetition of certain pattern. I'm just highlighting this particular certain pattern, which is repeated everywhere. So, it's a kind of a small cube I'm highlighting. This cube is repeated everywhere. We can see this. So, the repeated pattern, we call this as unit cell. Now, depending on the type of arrangement, there are total 7 basic Brevis lattices. Now, to remember the 7 basic Brevis lattices, the first type is cubic, where all 3 sides A is equals to B is equal to C, alpha is equal to beta is equal to gamma is equals to 90 degree. That's your angle. Tetragonal, A is equals to B but not equals to C. Alpha is equal to beta is equal to gamma is equals to 90. Orthorhombic, A is not equals to B, not equals to C, but alpha is equal to beta is equal to gamma is equals to 90. So all these 3, you will find all 3 angles are same, it's equals to 90 degree. Monoclinic, all 3 sides are unequal, one angle is unequal. But the most unsymmetrical structure is triclinic, where we have all 3 sides unequal and all angles are unequal, and even they are not equals to 90 degree. In case of rhombohedral, we have A is equals to B is equals to C, alpha is equals to beta is equals to gamma but not equals to 90 degree. And hexagonal, A is equals to B, not equals to C, alpha is equals to beta is equals to 90 degree and gamma is equals to 120 degree. Now we say there are 7 type of the Brevis lattices which are the basic one. These are the 7 one. But actual total Brevis lattices are 14. So because of this, as these each of the type is divided into subtypes. For example, in case of the cubic, we have simple cubic, we have body center and we have face center. So we shortly call it as SCC, BCC and FCC. Then in case of tetragonal, we have SCC and we have BCC. Orthorhombic, we have SCC, BCC, FCC. Along with that, we have ECC, that is edge-centered cubic. Monoclinic, we have 2 types, SCC and edge-center, ECC. In case of triclinic, there is only 1 type, SCC, rhombohedral SCC and hexagonal SCC. So if you count, this is 3 plus 2 5 plus 4 9 plus 2 11 12 13 14. So there are 14 Brevis lattices. But out of 3, we have focused only on 3 Brevis lattices, that is SCC, BCC and FCC. So let us revise all the aspects related to these 3 models. We know that in case of SCC, there are 8 atoms arranged at the corner of the cube. If we cut these corner atoms, we know that 1/8 portion of the corner atom comes in the unit cell. In case of BCC, there are 8 at the corner, 1 in the body center. So if you cut this particular crystal, 1/8 portion of this will come in the unit cell, while the body center, the entire atom will remain as it is. In case of FCC, there are 8 corner atoms and the 6 face-centered atoms. Each corner atom contribute 1/8 portion, while each face center contribute half atom to the unit cell. So if I talk about the number of atoms in the crystal lattice, here we have 8, but we have 8 corner atoms. Here we have 8 cornered plus 1 body centered atom. So that's total makes to be 9. Here we have 8 corner atom plus 6 face centered. So that makes total 14. Now number of atoms in the unit cell, this 8 contributing 1/8 portion, so 1 atom. 8 contributes 1/8 plus 1 entire body center, that makes 2 atoms. In case of this, 8 into 1/8 plus each of 6 contributes half, so 1 plus 3, that's total 4. Coordination number, if you talk about, look at this particular atom. It's having coordination 1, 2, 3. In the next crystal 4. This is 5 and there will be 6. So total coordination number will be 6. Here you can look at the body centered atom surrounded by 8 corners. So coordination number is 8. And here there will be 12. How 12? We can see 1, 2, 3, 4 corner atoms for this atom. Behind this there are 1, 2, 3, 4. So like that, in the next crystal there will be 4 face center that will be surrounding this face centered atom. If R is the radius of the atom and A is the edge length, then we have a relation A is equals to 2R for SCC. A is equals to root 3 4R by root 3, and in case of the FCC, A is equals to 2 root 2R. Now volume occupied to be calculated depending on how many atoms are there in the unit cell. So for one atom, if I talk about R is the radius and the atom's shape is a sphere, so volume occupied will be 4 by 3 pi R cube. So this is 4 by 3 pi R cube. Here there are 2 atoms, so 2 into 4 by 3 pi R cube, so that will be 8 into 8 by 3 pi R cube. And here there are 4. So 4 into 4, that is 16 by 3 pi R cube. Which when we'll convert into the percentage, we'll have 52.4% for SCC, 68% for BCC and 74% for FCC. So if you subtract it from the 100, we'll get 47.6% for void space for the SCC, 32% for the BCC, and the most closest packing, that makes to be 26% void space in case of FCC. Now in case of density, we have a simple formula, rho is equals to Zm upon Na cube, where Z is equals to 1 for SCC and A is equals to 2R. Here Z is equals to 2, A is equals to 4R by root 3, and here Z is equals to 4 and A is equals to 2 root 2R. So these are the different formulates that we have to focus while doing the CET for solid state. Now in next part, a quick revision for the packing in solids. In one dimension, we know that atoms are arranged in one axis. So if I talk about one of the atom, here the coordination number will be 2. Now this one-dimensional arrangement can be arranged on top of each other in such a way that atoms comes in contact with the atoms. So here if I call one layer as A, second will be A, third will be A. So we call this as AA type of packing. While here the atom is in contact with the depression of the another layer. So we call this as AB type of packing. Now in this case, if I talk about, the coordination number will be 4. While here the coordination number will be 6. If you join the surrounding atom, we get a shape square. That's why this is also known as square close packing. While here we get a hexagon shape, so we call this as hexagonal close packing. Now here the shape of the void space is square only, and here the shape of this void space is a triangles, but these triangles are pointing upwards and downwards alternately. Now if we continue this AA type of packing in 3 dimension, we get the coordination number 6, because in 2 dimension it will be 4. So one atom is coming above and one atom is coming below, and its own layer is having 4. So here the coordination number will be 6, which is same as the SCC model. Now in case of ABAB, when we arrange 2 layers of ABAB on the top of each other, there can be 2 voids possible. If 3 atoms come in contact with one atom, we call this void as tetrahedral void, because it's being surrounded by 4 atoms. While if 3 atoms comes in contact with 3 atoms, we call this as octahedral void, where we have a coordination number 6. So in case of this particular packing, if we cover the layers like AB type of packing, which will give us finally the HCP model, where the coordination number will be 12. While in case of if we pack the third layer as ABC, we'll get the FCC or CCP structure, where the coordination number will be again 12. In this case, we have to remember the first layer is similar to third layer, while here the first layer is similar to the fourth layer of the packing. Now in case of ionic solids packing, we have to remember that packing in the ionic solid, it depends on the various factors, depending on the charge on the ion, depending on the valency. So all these factors decides the packing in case of ionic solid. So depending on the octahedral voids, whether it is occupied, or tetrahedral void if it is occupied, the formula will decide that. For example, if I talk about a compound like NaCl, Na is plus and Cl is minus, the ratio is 1:1. So it is expected that Cl minus will form a structure, and in this particular structure, the Na plus will occupy the void. But since the ratio is 1:1, it is expected to occupy the octahedral void. But if I take example of calcium fluoride, calcium is 2 plus and fluorine is minus. The ratio is 1:2. So here the calcium would form the structure and the fluorine ions will occupy the tetrahedral voids, because the ratio is 1:2. So whether the ions are occupying the octahedral void or tetrahedral void, that is to be calculated from this ratio. Usually 1:1 is for octahedral void and 1:2 for the tetrahedral void. But I am taking 2 more examples over here, which you will find exceptional in case of the MCQ solving. First of all, I am talking about the cesium chloride. Here the ratio is 1:1. So we'll expect the chlorine ions will form the structure, and cesium is expected to go in octahedral void because the ratio is 1:1. But the cesium size is bigger and it's very difficult to accommodate in the octahedral void. Hence, cesium is expected to occupy the cubic void. So this is 1:1, but still the cesium going in the cubic void. That's one of the exceptional examples. Then zinc sulfide. Ratio is 1:1. Here the sulfur ions will form the structure, and zinc is expected to occupy the octahedral void, but the zinc size is very small. So rather than going in octahedral void, it goes in tetrahedral void. But if it goes in tetrahedral void, the ratio should be 1:2 or 2:1. But here we can see the ratio is 1:1. That's indicating the 50% of the tetrahedral voids are occupied. Next part is we can talk about the radius ratio rules, and we can find out the coordination number and the kind of the void space occupied in case of ionic solids. So there is a particular range that we'll decide. For example, if the radius of cation is divided by the radius of ion, then we have a ratio, suppose in the range of 0.155 to 0.225. The coordination number will be 3, and that void space will be trigonal planar. For example, like B2O3. If the range is between 0.225 to 0.414, then it will be coordination number 4. The void will be tetrahedral, for example, like zinc sulfide. If it is between 0.414 to 0.732, then it will be in the 6 coordination number with the octahedral void, for example, NaCl. And finally, if it is more than 0.732, the coordination number will be 8. That's cubic void, for example, cesium chloride. We are expecting the students to remember at least the range so that you can find it out in the answer for which kind of void spaces are occupied. Also, Remember these, at least these 4 examples, so that you can relate the structure of the unknown examples. For calculation or relation of the age length with the radius of the cation and anion, these are the 2 formulas which you will be specifically using for ionic solids. In case of FCC, R plus R minus, that is radius of cation plus radius of anion, that equals to A by 2. And this is R plus R minus, that is equals to root 3 A by 2. Next part is defect in the crystal lattice. Now, in exam point of view, just remember, we have studied in the syllabus stoichiometric defects. But for MCQ point of view, now you have to remember a different classification for the defects. Defects are classified into 2 types, stoichiometric and non-stoichiometric defect. Stoichiometric defect are vacancy defect. If the sum of the ions are missing from the crystal, we call this as the vacancy defect. In the vacancy defect, the density of the crystal is expected to decrease because ions are missing from the lattice site. In case of this particular defect, when it occurs in the ionic solid, we also call this as Schottky defect. Now, in case of interstitial, where the ions loses their original position and goes in the void space or the interstitial space, here density is expected to remain same. This particular defect, when occurs in ionic solid, we call this as the Frenkel defect. When the original site of the atom being substituted by the foreign particles, we call this as impurity defect. Now, if the impurity substitutes the original position, we call it as substitution impurity defect. And if it goes into the interstitial space, we call it as interstitial impurity defect. Now, in case of substitution defect, we have an example of a brass. In case of brass, the copper metal being substituted by the zinc metal. While in case of interstitial, we have example of steel where the interstitial spaces of the ion being occupied by the carbon. In case of the defects, it may happen due to the defect, the cation and anion, the numbers may not match. Let's have an example where we say the cations are more compared to the anions. Let's say in the anions are missing from the crystal, then we'll call this defect as metal excess defect because cations are more compared to the anions. In case of stoichiometric defect, whatever defect will occur, if that defect occurs with the cations, the same defect will occur with the anions also. That's why during this, the number of cations or the anions remain same. But in case of metal excess defect or non-stoichiometric defect, the cations and anions are of different number. But since they are different numbers over here, the electrical neutrality has to be maintained, and that can be maintained with the help of the position of the anion being taken by the electrons. Hence, this defect is also known as the F center defect. The meaning of F is a farb and the meaning of farb is a color. So this defect imparts color impurities to these substances. So remember, the F center defects are the metal excess defects where the defect occurs with the anion and the cation numbers are remain as it is. It may happen that the cations are less in numbers compared to the anions. Then such defects are called as metal deficient defect, where the neutrality to be maintained. Now here, as the anion positions are taken by the electron, here the cation positions are occupied by the remaining cation to be present in higher oxidation state. So if the one metal is present in +1 state in all metal in that crystal, you may find some of the metals are present in their higher oxidation state so as to balance the electrical neutrality. In case of the electrical properties, the metals are classified into 3 types. Elements are classified into 3 types: metals, semiconductors and insulator. We know that according to the band theory, the gap between the valence band and the conduction band is very small in case of metals. Hence, they are a very good conductor of electricity. You will find this particular gap is little bit higher in case of semiconductor. They are poor conductors of electricity, and very large in case of the insulator, and hence they are bad conductor of electricity. You can improve the electrical conduction of the semiconductors by providing the temperature where this gap between the valence band and conduction band can be overcome. But in case of insulator, even they are not a good conductor of electricity even on heating, because if you heat them, this particular gap, it's still not overcome. We can improve the semiconductors by means of a process called as a doping, where there are two type of doping possible. One is the intrinsic and one is the extrinsic. Now substances like silicon or germanium, which shows the type of behavior where the electrical conductivity increases with the temperature, because of more electrons can jump from the valence band to the conduction band. So this kind of doping, where you are providing just temperature to improve the conductivity, we call them as intrinsic semiconductors. Or you can add some foreign particles, so we call this as extrinsic semiconductors. If you put the impurity of lower group, so the lower group elements will be positively charged. So this type of semiconductors, we call this as the P type of semiconductors. Now impurity of lower group creates the acceptor level just above the valence band, and just the electrons jump from the valence to acceptor level. So that is creating a hole, positive hole, which is created in that valence band. While in case of N-type, the higher group elements are selected so that they will behave like a negatively charged particle. So we call this as N-type. For the P-type, generally from the group 13 having 3 electrons in the outermost shell, impurities are selected. While for the N-type, group 15 elements containing 5 electrons from the outermost shell are generally selected. Now, depending on the magnetic properties, we classify the substances into 3 types. Diamagnetic, which are weakly repelled by the magnetic field, do not have any unpaired electron, for example, like TiO2 or H2O or HCl or benzene. In case of paramagnetic, they are strongly attracted because of presence of the unpaired electron, for example, O2 or Cu2 plus, or Fe3 plus or Cr3 plus. In case of ferromagnetic substances, they show permanent magnetism. Now the reason for the ferromagnetism is that the solid state, the metal ions of these substances are grouped together into the smaller region. So each domain acts like a tiny magnet, and that will definitely create a strong magnetic field. You will find this strong magnetism even in the absence of the external magnetic field. For example, like Fe or carbon monoxide. So these are some examples of the magnetic properties of the solid state. The solution and colligative property. Now, well, first point that you have to remember for the MCQ point of view, you have to remember the formulas related to the methods of expressing the concentration. Now, for all these formulas, just remember: 1 symbolizing the solvent, 2 symbolizing the solute, W stands for the weight of the substance, capital M stands for the molecular weight, and small n stands for the number of moles. Now the percentage by mass will be the mass of that particular solute that you will calculate. So let's say W2 divided by W1 plus W2, that's a total mass multiplied by 100. In case of volume, it's V2 divided by V1 plus V2 into 100. While mole fraction, let's say I'm calculating this for the solute. So if I'm calculating for the solute is 2. The number of moles of the solute divided by total number of moles of solute in solvent. That's formula for the mole fraction for the solute. Now if I have to calculate for the x1, simply we can say 1 minus x2, because x1 plus x2, that has to be equals to 1. In case of molarity, we have a formula of molarity, that is number of moles of solute divided by the volume of solution, that has to be expressed in liter. Or we can say in case of N2, the weight W2 upon N2 into V. If it is expressed in ml, just multiply this by 1000. In case of molality, it's number of moles of a solute divided by weight of the solvent in kg. In case of normality, it's number of moles of the solute, but that has to be gram equivalent number. So that has to be W2 upon the equivalent weight of the solute. Generally, for the molarity, we take divided by molecular weight. Here we divided by equivalent weight multiplied by volume into 1000. So in case of the formula, that is ppm, parts per million. parts per million of these substances, it's nothing but the number of moles of that particular or number of substances, you can say mass of that solute, that's your W2. This has to be multiplied by 10 raised to 6 divided by the total mass of the solution. That's expressed in the the masses are expressed in the gram, or it has to be the same unit. Now mixing of solution, always remember, if you are calculating for the mixing, the relative mixing if you are calculating, so the molarity of after mixing the resultant solution will be M1V1 plus M2V2 divided by V1 plus V2, that's total volume. Similarly, you should remember some of the formulas which are relating the molarity and the molality of the substances. So molality, that small m, is always equals to molarity, that is divided by density minus molarity into the molecular weight divided by 1000. While molarity is equals to molality multiplied by density divided by 1 plus molality multiplied by molar mass upon 1000. So these are the some formulas we should remember, the relation between the molarity and the molality. Now in case of solubility of the gases in the liquid state, we should remember there are some factors affecting it. First of all, effect of the pressure. According to the Henry's law, the S is equals to K into P. That's indicating the solubility is directly proportional to pressure. As the pressure of the gas increases, the volume decreases, and hence it becomes easy for the gases to get accommodated inside the liquid. While in case of temperature, always remember the solubility is found to increase with the increase in temperature. So most of the time you can remember with the help of wherever the temperature is low, you will find the solubility comparatively it is very high. So solubility is inversely proportional to the temperature. You can remember one of the example, in case of seawater, we get more life down the seawater, right, and less life at the top. That is because the temperature is very high here. As the temperature high, the solubility of the dissolved oxygen in the water decreases. But at the bottom, as the temperature is very low, the solubility is more, and hence you get a more sea life. So remember, solubility is inversely proportional to the temperature. In case of the different colligative property, we have different formulas. Let us revise some of the terms related to that. First of all, we'll talk about the ideal solution. First property, lowering of vapor pressure. Ideal solution is the one which the molecules attracts one another with equal force irrespective of their nature. And hence, when you mix the two solutions, the volume of mixing, the delta V mix, it has to be equals to 0. Even the enthalpy change during the mixing has to be equals to 0. So there is no chemical reaction between the solvent and solute, and all this perfectly obeys the Raoult's law. For example, if you mix C6H6, that is benzene, plus C6H5CH3, that's toluene. So if you mix these two, they will create a solution which will be the ideal solution. But in case of non-ideal, those solution in which the interactions of the components are the different magnitudes, where the delta V of mix never be equals to 0, and even delta H of mixing will not be equals to 0, and these do not obey the Raoult's law. Now in case of formula, just remember there is a lowering of vapor pressure. So if the original pressure of the solvent is P0 and solution is PS, there will be lowering of pressure P0 minus PS divided by P0, that will be equals to X2. So that is to be calculated like W2 into M1 divided by M2 into W1. So this is the formula which we have to remember. We are going to use it for MCQ solving. Now the next part is elevation of the boiling point. The formulas to be remembered: delta TB, that is elevation, increase in the boiling point. So increase in the boiling point, so solution will have more boiling point. So this TB for solution minus the TB for that particular solvent. So I'm writing this as T0. That will be equals to Kb into molality. Kb is the molar elevation constant. So we can write this as Kb. Molality formula is number of moles, that is W2 upon M2 into the weight of the solvent. If it is not expressed in kg, if it is in a gram, multiply this by 1000. Now in case of depression of freezing point, the same formula, only the thing we write here delta TF. Depression in freezing point indicates the TF, that is of solvent, is more compared to the solution. So that's equals to Kf into molality. That's equals to Kf into W2 into 1000 upon M2 into W1, provided it's expressed in gram. In the next part, we are going to talk about the osmotic pressure. In case of the osmotic pressure, the pressure which is nothing but the mechanical pressure which must be applied on the solution to prevent the passage of solvent into the solution when the two solutions are separated from each other by the semi-permeable membrane. So if you have a semi-permeable membrane separating the two particular solvent, then let's say this is having low concentration and this is having high concentration, there is always flow from low concentration to high concentration, that solvents flows over here. When this particular solution passage of that solvent is stopped, there is something osmotic pressure is applied so as to stop that this thing. If the two solutions have the same osmotic pressure, we call those solution as the isotonic solution. If the two solution, one of them is having lower osmotic pressure, we call this as hypotonic. And if one of them is having the high osmotic pressure, then we call this as the hypertonic solutions. Now in case of osmotic pressure, we need to remember the formula which will help for the MCQ. Pi is equals to CRT. So this pi is the osmotic pressure, C is the concentration, can be expressed in different ways that we have studied. R is the gas constant and T is the temperature. But always remember, there is always the abnormal osmotic pressure or osmotic behaviors being observed. Now what happens when you have a solute, or if you talk about a simple electrolyte, if you dissolve this electrolyte into the water, there are two types of the mechanisms work. Either there can be association or there can be dissociation. Now due to the association, what happens, the property of the simple molecules, so as they associate, the number of particles becomes less. In short, the colligative property is something which is depending on the number of particles which are present and irrespective of their nature. So in case of association, the number of particle associates, because of the number of particles in the solute becomes less, and since the number of particles less, the colligative property also decreases compared to the standard value. In case of dissociation, the particles increases, and that's why they show some abnormal behaviors compared to the standard things. So abnormal behaviors of these electrolytes can be compared by calculating just Van 't Hoff factor, where the Van 't Hoff factor I is equals to the observed colligative property divided by the theoretical one. Theoretical one, it's something which is generally calculated with respect to the non-electrolyte. So if I have to calculate I for the pressure, so this is lowering of vapor pressure delta P observed divided by delta P, which is for the theoretical one. Also that is equals to delta TB observed one divided by delta TB, which is theoretical one. You can write this formula with respect to the freezing point also. So this is theoretical and this is observed. Also pi observed divided by pi theoretical. But this is inversely proportional to the molecular weight. So for the molecular weight, it will be molecular weight theoretical upon molecular weight observed. So these are the certain formulae that we have to remember while doing or solving the MCQs which are related to solution and colligative property. Also, when I'm talking about the degree of dissociation, can be related to the Van 't Hoff factor, can be related to the degree of dissociation. If we are talking about a property such as like association and dissociation, let's say for the dissociation, always remember I will be equals to 1 plus 2 alpha. This is a formula we'll be using for the degree of dissociation and the Van 't Hoff factor. While for the association, I will be equals to 1 minus alpha divided by 2. So these are some formulas which are very important when we are solving the MCQ related to the association and dissociation of the particles. Let us talk some important points related to the thermodynamics. First of all, we'll focus on the intensive and the extensive properties which are depending on the amount of the substances. Now when it is not dependent, do not depend, or simply the in stands for independent of the mass, we call this property as the intensive property. For example, the properties are like pressure or density or the concentration or the temperature. These are not property depending on the amount of substances. So we call these as the intensive properties. In case the extensive properties, these are totally depending on the amount of substance. Hence, we call this property as the extensive property, like mass or volume or heat, quantity of heat. All these properties are depending on the amount of substances. Now the type of processes, we already know isothermal, where the temperature remain constant. So we have to remember delta T will be equals to 0. Now the temperature somewhere related to the internal energy of the system. So delta U will also be equals to 0. In case of adiabatic process, the heat exchange will be constant. So we say Q is equals to 0. But in this case, remember delta T is not 0, delta U is also not 0. In case of isochoric process, the volume remain constant, so delta V is equals to 0. Somewhere we have a formula of W is equals to P delta V, therefore W will also be equals to 0. And here the heat exchange can also be equals to the internal energy. In case of isobaric process, where the pressure remain constant, so delta P is equals to 0, which is nothing but the Q is somewhere related to the delta H. So remember, for isochoric process, delta U is equals to the heat exchange at the constant volume, while delta H is the heat exchange at the constant pressure. For the cyclic processes, the series of changes of the state and finally returns to the initial state is called as a cyclic process, where the delta, that is state function, that equals to 0. So in short, delta V is equals to 0, delta U is equals to 0, and delta H also equals to 0. Reversible process, where the driving force and the opposing forces differ in infinitesimally small amount. So they are very slow process, hypothetical, ideal, non-spontaneous processes. Maximum work is obtained under the reversible process. Driving forces, and if the opposing forces they differ by the fixed amount, we call this as irreversible process, where the system and the surrounding are in equilibrium only in the initial and final state. They are comparatively fast, finite times of completion, practical, real, and the spontaneous process. No maximum work can be obtained during this. Now, some of the formulas we should remember for work done calculation. For example, for any irreversible processes, remember that's not a maximum work done. So W is equals to minus P delta V. But in case of the reversible process, which is the formula for the W max, that's equals to minus 2.303 nRT log to the base 10 V2 upon V1, that's equals to minus 2.303 nRT log to the base 10 P1 upon P2. So volume and pressure can be related to the work using this formulas. Also, while doing all this calculation, you need to remember some of the conversions, like 1 liter atmosphere is converted into 101.3. This is the conversion term that we can use for converting liter atmosphere into the joule calculation. So 1 liter atmosphere, that's equals to 101.3 joule. Next is in case of internal energy. Internal energy is denoted by U, is actually consisting of two type of energy. One is the kinetic energy and one is the potential energy. When we talk about the kinetic energy, that's consisting of translation energy, then that's consisting of vibrational, or that's consisting of rotational energy, or that must be consisting of the electronic energy. In case of the potential energy, always remember this is something related to the intermolecular energy, or it is maybe related to the intramolecular energy, or maybe related to the nuclear binding. So these are the internal energy types that we have to remember. And magnitude wise, you always remember the trans is having more magnitude, then vibrational, then rotation, and lowest energy you will get it from the electron. Just MCQ point of view, you should remember this. Now, in case of first law of thermodynamics, we know all the statements that energy neither be created nor be destroyed. It can be converted from one form to another form. Now, we have to focus on a mathematical form of this equation. Delta U is equals to Q plus W. Now, here, in case of different things, if the Q is positive, heat is absorbed, negative, heat is evolved. In case of W, if it is positive, then the work done on the system, and if it is negative, the work done by the system. Now, under different processes, how this equation is going to change, that's very important. For isothermal processes, the delta U is equals to 0, Q will be equals to minus W. For adiabatic process, Q will be equals to 0, therefore we'll write delta U is equals to W. Isobaric process, here delta P will be equals to 0, so W will be equals to minus P delta V, that will remain as it is. In case of isochoric, where the delta V is equals to 0, so W will also be equals to 0. So these are different formulas related to the first law of thermodynamics. Next, in case of enthalpy, we have a formula H is equals to U plus PV. If you calculate for the different state functions, we'll get a delta H is equals to delta U plus P delta V. This is a formula which is related to the work done. We can use it. But if the enthalpy of the reaction is to be calculated with respect to any chemical reaction, we have to use formula delta H is equals to delta U plus delta nRT, where the delta N is number of moles difference between the reactant and the product, provided the reactant and the products are present in the gaseous system. Little bit some information about each one of this term. For example, like enthalpy of formation. Enthalpy of formation is nothing but the enthalpy which is accompanying the formation of 1 mole of a substance in its standard state. So generally MCQ wise the question comes on the enthalpy of formation, that identify the reaction which is the enthalpy of formations. For example, if I have to identify the reaction for related to the methane formation, always remember there should be carbon plus hydrogen in their elemental state. Though I know the carbon and hydrogen can't react to give the methane, but always remember the enthalpy of formation reaction should always consisting of the product which is formed from its element in their standard state. So if I have to find out the equation for the H2SO4, I will write H2 plus S2 plus twice of O2, which is practically not possible, but this is the equation for the standard enthalpy of formation. So it is always remember the product has to be formed from the reactant in its standard state. Now next is the standard enthalpy of combustion, which is accompanying the 1 mole of a substance in its standard state when it is burned in excess of the oxygen or the air. You will find this enthalpy of combustion is always a negative. Okay, but there are some reaction when the combination of oxygen will leading to the combustion where you will find delta H positive. So remember these two examples, N2 plus O2 giving twice of NO and F2 plus half of O2 giving OF2. Both these reaction where you will find delta H positive. So these are exception one. Otherwise, enthalpy of combustion you will always find the value to be negative. Enthalpy of neutralization, it's the enthalpy accompanying the neutralization of 1 gram equivalent of an acid by 1 gram equivalent of the base in the dilute solution. For the strong acid and strong base, always remember this enthalpy of neutralization will be always equals to minus 13.7, that's kilocalorie per gram equivalent, or that's equals to minus 57.32 kilojoule per gram. So this particular standard value will be always for the strong acid and strong base. Now the compounds with the positive value of this is for the strong acid and strong base containing H plus and OH minus. Next is a bond enthalpy. Bond enthalpy is nothing but the enthalpy change which is necessary to break particular bond. So if you are calculating the heat of reaction using the bond enthalpy, always remember it is heat of reactant minus heat of product. If I am calculating the enthalpy related to the enthalpy of formation, always remember delta H is equals to heat of product minus heat of reactant. So these are some formulas related to this we have to remember. Now just a little bit a quick revision of the definition. Heat of fusion, that's 1 mole of a substance. When it is melted, it's called as fusion. Enthalpy of vaporization, 1 mole of a substance or liquid which is vaporized is vaporization. Enthalpy of sublimation, 1 mole of a substance converted into the gaseous phase. Ionization is nothing but the removal of an electron from each atom from 1 mole of a gaseous substance. Electron gain enthalpy, it's a enthalpy related to the 1 mole of a gas when they gain electron in the outermost shell. And enthalpy of solution, that's a dissolution of 1 mole of a solute in around 1 liter of a solvent. We call it as the enthalpy of the solution. The next part that we'll be focusing, that's the heat capacity. Heat capacity is generally denoted by the symbol C. Heat capacity is nothing but the amount of heat which is required to raise the temperature of the system through 1 degree or 1 Kelvin. The unit of this is generally joule per Kelvin. Now this can be expressed in two different ways, that is heat capacity at constant pressure and heat capacity at constant volume. When I'm talking about the Cp, Cp is always equals to delta H upon N into delta T, while Cv is always equals to delta U upon N into delta T. Cp minus Cv, that's equals to R. Also remember the Cp divided by Cv is equals to gamma. If gamma is equals to 1.33, this is particular value we have to remember, the molecule will be triatomic. If it is 1.40, the molecule will be diatomic, and 1.66 for the molecule to be monoatomic. So these are the values which are to be remembered while calculating whether the substance is monoatomic, diatomic, or whether it is triatomic in nature. Now in case of the Kirchhoff's equation is nothing but delta H2 minus delta H1 divided by T2 minus T1 is equals to delta Cp. So this is nothing but it gives the effect of temperature on the heat of reaction at the constant pressure. Also remember delta Cp, it's a constant volume. This is something the formula which we can use when this particular Kirchhoff's equation is for the constant pressure. We can use it for the constant volume also, and there we can use delta U2 minus delta U1 upon T2 minus T1 is equals to delta Cv. So these are some Kirchhoff's equation derived formulas we can use. In case of Hess law, we know that whether the reaction take place in one step or the two step, the final heat of reaction is always a combination of different steps. For example, if I'm saying A is giving B, B is giving C. This is having delta H1 heat of reaction, this is delta H2. If I'm to calculate for A is equal to C, delta H, then delta H will be equals to delta H1 plus delta H2. That's the Hess equation. Most of the problems related to the Hess law can be asked. The spontaneous and non-spontaneous process. The process which occurs of its own, no external forces are required, we call it a spontaneous process. And the one which occurs or requires the external forces to occur, we call them as non-spontaneous. Now in this case, the entropy plays very important role. Entropy is nothing but the randomness. So solid, when it is turning to liquid and then it is turning to the gas, the entropy of system, that is disorderliness, is always increases. Entropy of the system is generally calculated by using heat reversible upon T. So it's directly proportional to the heat provided and inversely proportional to the temperature at which this system is already present. Now we can relate this this entropy to calculate the spontaneity and the non-spontaneity of the system using the second law of thermodynamics. According to the second law of thermodynamics, the spontaneous heat flow is always unidirectional. That is, always the spontaneous heat flow will be from high temperature to the low temperature. In case of the heat cannot be completely converted into work without producing the permanent changes either on the system or on the surrounding. So no machine in the universe has the 100% efficiency. So delta S for the universe is equals to delta S of the system plus delta S of the surrounding. If this is greater than 0, if it is positive, then this reaction is said to be the spontaneous. So we have a rule to identify the spontaneity of system when the delta is total, that is system plus surrounding. If it is positive, the reaction is spontaneous in nature. But according to the thermodynamics, the thermodynamic is always deals with the system, not with the surrounding. So this particular rules fails under the criteria of the thermodynamics. So we need a term which will only define the system, not the surrounding. And hence we have introduced a term that is Gibbs energy. So Gibbs energy is equals to delta G is equals to delta H minus T delta S. So we can use this particular formula. So if the delta G is a negative, the reaction is said to have the spontaneity. And if it is positive, the reaction is non-spontaneous. So we can have a different relation using this formula. So remember, if delta H and delta S, if both are negative, then the delta G will also be negative. So reaction will be spontaneous at all, that is comparatively delta H should be less than the T delta S. So this reaction will be spontaneous. Then delta H and delta S, if both are positive, then delta G will be negative only, and this reaction will be again the spontaneous, provided the T delta S has to be greater than delta H, while here the T delta S has to be less than delta H. Let's say if the delta H is negative and delta S is positive, then the delta G value will always be negative. So it's always spontaneous. And if this is delta H is positive and delta S is negative, delta G will be positive and this is always non-spontaneous. This kind of questions can be asked related to the MCQ. So we have to remember this, how the spontaneity changes with respect to the Gibbs energy. Also related to the Gibbs energy, how we can equate it with the equilibrium. Always remember, delta G0 is equals to minus 2.303 RT log K. So equilibrium constant can be related to the delta G value using this equation. So you need this particular formula while solving the MCQs related to the Gibbs energy. Now the last additional points and some third law of thermodynamics. So third law of thermodynamics is something which is dealing with the entropy of the perfectly orderline crystal substance, which is always found to be 0. That is, S is equals to 0 if the absolute temperature is 0 Kelvin. So it's important, it allows to determine the absolute entropy of the system, because delta S is equals to, that is at S is that particular temperature minus S0. But S0 is 0. At 0 degree S is 0. That's why that is equal to just ST. So that's entropy at the of the system at present at that temperature. So this is Cp dt upon T. Now additional information that you should remember for the solving MCQs. First of all, internal energy is the change is heat evolved or the absorbed at the constant volume, and it is found by using a bomb calorimeter. So internal energy can be calculated using this bomb calorimeter, which works with the formula that is delta U is equal to C, that's heat capacity, multiplied by molecular weight upon weight of the substance into delta T. So this is the formula you'll be using for the bomb calorimeter. Also, the calorific values. The calorific values are generally for the fuel or the food is generally divided by calculating the heat in calories, which is obtained per by this you can say by combustion of 1 gram of that fuel or a food. So that heat evolved during that process to be calculated. Also, we have to remember for the Carnot cycle. Carnot cycle it's a cyclic system which returns to the original state after undergoing the number of successive changes. The most common example is the Carnot cycle. Just remember, in stage 1, it's an isothermal expansion. Then it's stage 2, that's the adiabatic expansion. Stage 3, it's isothermal compression, and stage 4, it's adiabatic compression. So finally the system comes to its original position where it's called as the cyclic process. Let us talk about the different important points related to the electrochemistry. First of all, let us revise the formulae which we required for the resistance and conductance for calculations. First of all, resistance is equals to the resistivity multiplied by L into A. Exactly opposite formula you will get for the conductance. So in case of the conductance, that is G will be equals to, that's your conductivity, that's K, multiplied by A upon L. So we can say this formula is nothing but conductivity if we calculate. The K is equals to G into L upon A. Now while doing the calculations, we have to remember the conductivity K is generally, this is called as the cell constant B, and G is nothing but inversely proportional to the resistance. This formula is very important when I am talking about the MCQ point of view while calculations. Now in case of molar conductivity will be equals to, that's K into 1000 upon concentration. That may be expressed in molarity. Cauchy's law, the limiting molar conductivity of electrolyte, it's the sum of the limiting ionic conductivities. So molar conductivity, that's highest 0, that's equals to the contribution which is given by the cations plus the contribution given by the anions, because each contribution is independent of each other. In case of application of Cauchy's law, remember we use this for calculating the molar conductivities for any electrolyte at the 0 concentration. Especially for the weak electrolyte we use this. We can relate this conductivities, molar conductivities, with the degree of dissociation. Alpha is equals to molar conductivity divided by maximum molar conductivity. Also the K, that is dissociation constant, is equal to molar conductivity square into C divided by molar conductivity 0 into molar conductivity 0 minus molar conductivity. So these are some formulas that we need for solving the MCQ related to the electrochemistry. Electrolytic cell, the conversion of the electrical energy into the chemical energy. So remember here the cathode will be negatively charged where the reduction will occur, and anode will be positively charged. Here we can have the electrical energy, different examples where actually we just allowed the reaction such as non-spontaneous reaction by passing some electrical current through this. So some of the products we can remember, if I take a molten NaCl, so what I'll get at the cathode and what I'll get at the anode. So if I talk about molten NaCl, I'll get the sodium and the chlorine gas at respectively anode. Instead of this, if I take aqueous NaCl, then I'll get hydrogen gas at the cathode and the chlorine gas at the anode. If I take molten NaOH, so here I'll get sodium at the cathode and oxygen at the anode. But if I'll take aqueous NaOH, then I'll get a hydrogen at the cathode and oxygen at the anode. One of the important example, just remember aqueous H2SO4, where you will get hydrogen gas at the cathode and oxygen gas at the anode. In case of voltaic cell, where the conversion of chemical energy into electrical energy, where some spontaneous reaction occurs of its own so as to give the product. Here, remember, the cathode is positive and the anode is negative. Now, the particular examples like Daniell cell you can remember. Then salt bridge, connecting the two solutions to avoid the direct contact of the electrolytes and maintain electrical neutrality. Also minimize the liquid junction potentials. Now next important part for the MCQ point of view, that's a Faraday's law of electrolysis. The first statement, the first law, that's the amount of the given product liberated at the electrode during the electrolysis is directly proportional to the quantity of electricity passed. So we generally write this as amount of substance which is deposited is directly proportional to Q. So M is equals to Z into Q, where Z is a electrochemical equivalence. So finally we have Z, M is equals to Z, Q is I into T. So this is a formula we can use for calculation. Now in case of the second law, when the same electricity is passed through the solution of the different electrolytes, the amount of substances liberated at the electrode are directly proportional to their chemical equivalence. So M1 is directly proportional to E1 and M2 is directly proportional to E2. Therefore, we can say M1 upon M2, that is masses deposited at the electrodes, is equals to the E1 upon E2. So these are the two formulas that we have to remember. Also here just remember the Z is nothing but the electrochemical equivalence, which can be calculated by using the formula E upon 96,500. So that's formula for the Z. Next part is a classification of electrodes. Electrodes are classified into different types depending on what kind of combination we have. We can have metal ion electrode, where the metal, let's say for example zinc, will be dipped in ZnSO4 solution, that is electrolyte of its own. We can have a second type of electrode where, example like gas electrode, or we can call this as non-metal ion electrode. For example, like chlorine gas, for the electrical contact we'll use platinum that will be in contact with the chloride ions, for example like HCl if we take the aqueous. Then we have third one, that's sparingly soluble salt electrode, where there will be some metal, let's say for example like mercury. For electrical contact will provide platinum because mercury is in liquid state. It will be in contact with its salt like Hg2Cl2, but it's sparingly soluble. Hence, we'll take one more electrolyte which is containing the anions. For example, the chlorine ions are present here. And the fourth type of electrode, which is nothing but redox electrode. Now, in case of redox electrode, for example, like Fe2 plus ions in contact with Fe3 plus ions, For the electrical contact, we use platinum. Now, in case of the cell presentations, we can use this particular different electrodes for the combination. So, single vertical line, that is indicating the boundary between the metal ions and its electrolyte. So, if I have to combine the two things, for example, zinc solid in contact with Zl2 plus solution. So, this is indicating the zinc is in contact with its own ions. You can provide the concentration of this particular solution. Double line will indicate the separate or the salt bridge. Let's say copper 2 plus ions are in contact with the copper electrolyte. So the electrode which is present on the left hand side, it's presenting the anode where the oxidation will take place, and the the electrode which is present on the right hand side, it's the cathode where the reduction will take place. So these are different terms, or these are the different criteria you have to use. Now from this I can understand zinc is undergoing the oxidation and copper is undergoing the reduction processes. The next part is important for the MCQ point of view. That's the Nernst equation. We should remember. First of all, for the standard thing, E0 cell will be equals to E0 cathode minus E0 anode, provided they have given you the reduction potentials. Also, the EMF of the cell will be equals to E0 cell minus 0.0591 upon N log to the base 10, the oxidized state of that substance upon the reduced state. Okay, so this is the something we have to use. For example, metal, let's say solid, is undergoing the oxidation. It's losing n number of electrons. We'll get M by losing n number of electrons. So this E will be equals to E0 cell minus 0.0591 is losing n electrons log to the base 10, this oxidized state, so concentration of Mn plus upon concentration of M. But here we can see the M is in solid state, so its concentration can be taken as unity. So it's nothing but E0 cell minus 0.0591 upon N log to the base 10 M N plus concentration. We can also relate this to the Gibbs energy. Delta G will be equals to minus N E cell into F, that's Faraday's constant. Also delta G0 is equals to minus N E0 cell into F. So we can use these two formulas for relating to the Gibbs energy. Now there are two different type of the electrodes. One is the indicator electrode, whose potential is totally depend on the concentration of the particular ion which are present in the solution. While in case of reference electrode, the electrodes which are arbitrarily chosen and the potentials are fixed, we call them as reference electrode. Now in case of reference electrode, we have to remember two examples. First is SHE, standard hydrogen electrode. It's a primary reference electrode. That primary, that means this particular electrode is very difficult to set up, and you have to determine its potential by setup of a certain equipment. Representation of the cell is done by H plus aqueous having 1 molar concentration in contact with the hydrogen gas having 1 atmospheric pressure, this is in gaseous state, in contact with the platinum. You can write the anodic reaction, that's oxidation reaction, half H2 gaseous state giving H plus aqueous plus electron. Opposite reaction if you connect this as a cathode. This potential of this is generally taken as 0. The standard EMF of this reaction is taken as 0. Also the calomel electrode, that's also one of the important reaction. In case of calomel, calomel cell is called as a secondary reference electrode because its potential is generally determined using standard SHE. It's metal sparingly soluble salt electrode presented by KCl, which is aqueous in contact with He2Cl2 solid in contact with mercury, which is in liquid state for the electric contact provided platinum. Now the concentration of KCl will decide the reduction potential of this particular calomel electrode. For the 0.1 normal solution, generally it is found to be 0.333. For the 1 normal solution, it is found to be 0.28, and when it is saturated, it's found to be 0.242. So these values are fixed for the calomel electrode. EMF series is nothing but the elements are arranged in the form of the electrode in the decreasing order of their standard reduction potentials. Hydrogen has a standard potential 0, so it's generally kept in between. Elements with the positive standard potentials are placed above, and decreasing, so remaining are below. So we have to remember the EMF series has different application, including the spontaneity of the reaction can be checked. Spontaneity can be calculated if the E cell, if you get it positive, the reaction is spontaneous in nature. Also, in order to predict the oxidizing and reducing agent, the elements which are present above the hydrogen, they have the positive electrode potential. They are all are good powerful oxidizing agents, while which are below hydrogen, they are good reducing agents. So these are the properties which we can use as application for the different EMF series. Whether also we can understand whether the metal can displace the hydrogen or not. So remember, the one which are present below hydrogen, they can displace hydrogen from aqueous solution, and this cannot displace the hydrogen from the aqueous solution, the metals which are present above hydrogen in electrochemical series. Now, type of the galvanic cell, there are two types. Primary cell, it is the electrochemical cell in which the electrical current is generated within the cell itself. For example, we can we can remember the Daniell cell. The Daniell cell where the zinc is made as an anode in contact with the ZnSO4 solution, aqueous, in contact with the copper sulfate, with the copper is made up as the cathode. Potential of this Daniell cell E is found to be 1.1 volt. Secondary cell is an electrochemical cell in which the electrical current is not generated within the cell, but it is previously stored from the external source during the charging. So we can remember example of the storage. They are kind of like a storage cell, like a lead accumulator. So in case of lead accumulator, remember it's a charging discharging process. So during the charging process, this particular cell is made by Pb in contact with PbSO4. So this is made as an anode in contact with H2SO4 solution, which is generally 38% weight by weight percent is taken, in contact with PbSO4, which is solid, PbO2, which is made as a cathode, and in contact with Pb. So charging discharging processes of the lead accumulator is to be revised. So there are two types, primary and the secondary cell of the type of the galvanic cell. Fuel cell is very important with respect to the generation of the electricity and the water also. So here what we do is hydrogen is bubbled through its H plus aqueous solution containing NaOH, little bit of basic media, contact with OH minus, and O2, which is at the graphite. Both these electrodes are made up of the graphites. So this is negative and this is the positive electrode. So here what happens at the anode, that is hydrogen is bubbled. So the hydrogen in this aqueous media is converted into water by loss of electrons, while at the cathode, oxygen in the water gains electrons to give OH minus ion. So this is overall process. If I talk, it's twice of H2 plus O2 generating the water along with the EMF of cell, which is generated. It's 1.299 volt. So this much of current is produced during this reaction. The last part that we'll be revising is a corrosion, which is a process of the tearing or wearing away, the gradual decay of the destruction of the metals when it is exposed to the atmosphere, especially if it is a moist air or something. Corrosion of the iron, it's one of the important example where iron undergoes the oxidation process with the loss of electrons. So some of the surfaces of iron acts like the anodic surface in presence of a moisture. Now water in acidic media will dissociate into H plus and OH minus. This particular H plus and OH minus, this is generating the oxygen or water in this case. So twice of H plus plus half of O2 from the atmosphere will gain electrons, twice of electron to generate the water. So this Fe is then turning 2 plus, will further turn to the Fe3 plus, and this Fe3 plus will turn to Fe2O3. The hydrated form of this particular Fe2O3 is called as the rust. This can be avoided, factors that is corrosion can be avoided by alloying of metals, polishing the surfaces, production of the insoluble oxide coatings, electroplating, metal spraying, galvanizing, removal of string. So with the help of that we can remove the rusting, or we can avoid the corrosion processes.